Hi, everybody. How's everybody doing today? Well, I have a lot to talk about. I've been given 3 hours. I'm gonna try to make it so that you don't fall asleep. Let's hope this is gonna be interesting. The presentations that I have prepared in covering 4 topics. Basically, I'm going to do an overview of the Rust programming language and some of the key features that I find myself very useful, and some of the features that we use inside of Kaspa and that I use in a variety of projects. And then we're going to basically transgress that into overview of Kaspa SDK, which is based on Rust and uses these Rust technologies. We're going to then take a small, maybe 10-minute break, just so that I don't lose my voice. And then we're going to do 2 sessions. One, basically do an overview of approaches in layer 1 Kaspa, basically smart contract design, and different techniques and goals behind that, and then do an overview of layer 2 that we have been prototyping, and that is currently in the middle of basically a research phase, and where we're working toward specifications for basically both L1 and L2 as well. So I'd like to say thank you to Kaspa Ecosystem Foundation for inviting us. It's been a fun trip so far in Hong Kong. I'd also like to thank the developers and people in the Kaspa ecosystem, the developer ecosystem that I have been working with over the last 2+ years, from whom I learned really a lot, and who's been really helpful to me. And in general, it has been really a joy and a pleasant experience to work with. So a little bit about myself. My name is Anton. I am known as Aspect in Kaspa ecosystem. I've been involved in software development since 1988, many years. My sort of interests over the years and the work that I've been doing have included such elements like computer graphics, visual effects, 3D graphics, virtual reality, high performance GPU processing in the area of computer graphics, embedded mobile systems, content delivery systems, virtual machines and operating systems, industrial automation, financial data processing, and over the last decade, basically cryptocurrency technologies and smart contract technologies. And I strongly believe in sharing the knowledge to empower the developer ecosystem around, and a lot of my contribution to the cryptocurrency ecosystem as a whole in revolving around basically propagating the knowledge, know-how of different cryptocurrency technology that I had the privilege to be involved with. So my career can pretty much be split into about 3 decades. In the first decade, I've been involved in visual effects and computer graphics. The software that I have developed has been used to create special effects in shows like Star Trek Voyager, movies like Armageddon with Bruce Willis, and the friendly ghost named Kat. Interesting. Over 20 years basically 25 years later, there is Casper, which is a meme coin that is on Kaspa chain. Last decade, I've been working in the area of content delivery systems, where I've been doing adaptation of basically a multi-million dollar content delivery systems to work on consumer grade hardware using GPUs and pioneered variety of technologies as well as were the first technology to deliver high definition content in stadiums. And these are very much mission critical applications because a failure of a system can render a stadium inoperable, which then results in a potential loss of advertisement revenue, which can be a typical game advertisement revenue, about $30 million. After that came Bitcoin. I've discovered Bitcoin. I got very involved in actually initially Litecoin project and then in Bitcoin ecosystem, helping Bitcoin Core. And I was through a different set of circumstances. I was privileged to have co-founded and for basically 5 years ran an international academic conferences called Scaling Bitcoin, which we launched in Montreal in 2015. And then in December 2015, we ran an event here at Hong Kong Cyberport. We then did an event at Politecnico di Milano, Stanford University, Keio University in Tokyo, and Tel Aviv University. And if you look at the last picture here in Tel Aviv on the left side, that's Jonathan Sapolsky, the creator of, the founder of Kaspa. And right next to him is Aviv Zohar, who is the basically co-creator of the Ghost DAG. And between them is my girlfriend. And basically, they've been extremely helpful in facilitating our event in Tel Aviv as a local host organizer, where we brought all the researchers from international, basically international research community, research and development community in the area of Bitcoin and advanced cryptocurrency technologies. If you are interested in a cryptocurrency, Bitcoin, or a variety of advanced technologies, there's a YouTube channel which can be found on scalingbitcoin.org. It has all the sessions recorded. And at Stanford in 2017, as we had a lot of basically a lot of developers and researchers coming to one place, we have organized a bootcamp called Bitcoin Edge, which really is scaling. After that, it started in Stanford, in Keio, and in Tel Aviv for 2 days, where developers shared their knowledge and created educational courses covering all aspects of basically Bitcoin related technologies. And Kaspa has its lineage in Bitcoin. It's a very much based on, it's a UTXO system that uses the same technology in the area of wallet processing, some of the internal consensus processing. So if you want to learn about some of the internals of Kaspa, you can also study some of the internals of Bitcoin. There's a lot of technology related to that. Roughly a bit over 2 years ago, as Sutton started rewrite, well, before that, I got involved with the Kaspa project. As I knew Jonathan and I saw them trying, unfortunately, well, at that time I was based in Canada. Now I am in Europe. But as they were developing Kaspa Node software, and I was kind of following the research and development efforts, I saw that this was basically a kind of a server type, a command line application, and command line application is something that is difficult to. Hold on a sec. Let's just put it here like this. Looks good. It's powering. So the command line application is great, but it makes it difficult to use to certain level of computer users who maybe are proficient with just general computer use and want to participate in the ecosystem and want to run the node, but they do not necessarily know how to use command line. They're not that advanced type of a user. So to kind of mitigate that and to also make this more accessible to users who don't want to fiddle with tech, I've created a small wrapper software called KDX, which integrated the Kaspa wallet as well as a web wallet, and then some of that internal code was turned into an SDK, which was then basically the Kaspa JavaScript and TypeScript became Kaspa JavaScript and TypeScript SDK. And a little jumping forward, there were a lot of problems with that SDK. It required, whenever changes were made in the core client, Golang client, we had sometimes the developers would make changes and not even advise anybody because there were different groups. And then the SDK would have problems working with the software. There was this disjoint kind of situation and lack of communication and such, which down the road falls into what I am about to talk about with regards to SDKs. So then Michael Sutton has started the Rusty Kaspa project. I helped at the very beginning, but then I was not available for a while. But the team that was working on that, George's, Tiram, Michael, Ori, they were doing different parts. Some parts I was not involved in, but some parts because at this point I already had a few years of experience in Rust. I tried to give some advice and such, and gradually over time kind of got pulled into contributing to core and doing more and more work. And there were things to be done, but so kind of nobody to do them. So I was taking these things upon myself and gradually became more and more involved. So some of the things that I have done in the Rusty Kaspa is I have co-designed the RPC infrastructure together with George's. I've supported Michael and Ori and General, basically testnet 11, Rusty Kaspa deployment and testing, debugging a few complex things in the early days where we had different interlocking problems. I have then taken kind of the project that we had and started moving it toward it becoming more of a framework that is generally usable. So now Rusty Kaspa is not just an application, a node, but a framework of tools that are usable from Rust. So we build up gradually, and this is always work in progress. Everything is ever finished. There is now Rusty Kaspa SDK, as well as WebAssembly WASM32 SDK that allows this SDK to operate in TypeScript and JavaScript environments. This is basically the main focus of this presentation. I provided the different support and coordination within the core ecosystem, and I have then utilized all these tools that we have developed in Rusty Kaspa to develop a next generation client called Kaspa Next Generation, Kaspa NG, to replace eventually KTX, which is very whereas KTX was a kind of accessibility effort to make the node accessible as a desktop application, similar to like Bitcoin Core desktop wallet. Kaspa NG is much more of an advanced application, which is very heavy security focused, and it is 100% developed in pure Rust. This application is unique in a sense that it is a single code base, which can be run as a desktop application as well as web application. So the first, that was basically the intro to what I've done in the past. The first talk is building a modern multi-platform SDKs in Rust. Key features in the Rusty Kaspa Framework SDK. It's kind of two presentations that I baked in one because one set of topics transgresses into the other. So a little bit about the Rust programming language. I basically became sort of a evangelist, I guess, over the years. As I mentioned, I've been doing software development for 3 decades, and I started in '88 with C, and pretty much all of my development experience has been revolving around development in C++. I've built very large and complex frameworks. I've managed teams building frameworks. And I can say that over the entirety of my career, I have easily spent anywhere between, it's hard to really say, but just to throw it out there, I'd say between 3 to 6 months of my time actually dealing with various bugs and problems that were introduced by C++ development. All the standard things that Rust basically initially set out to do, which is memory leaks, race conditions, the variety of memory overrides, a variety of problems. And Rust kind of mitigates all that. So I have actually, before Kaspa, I kind of reduced my development. I was focusing on other things and was not developing as much, but at scaling kind of completely independently, Rust was being adopted, and a number of people who I very much respect have spoken very highly about Rust. So I have one said that, another said that, and at some point I said, well, this is something I have to look into because just too much information coming from different directions that really was signaling to me that something I should get into. And I've seen that before with other developers, but I was too ignorant and was not paying attention. And I regret that because it would have changed much earlier. So Rust began in 2006 by a Mozilla research employee, Gaten Hoare. named after the group of fungi that are over-engineered for survival, Rust. Mozilla started sponsoring the project in 2009 with different people. And in 2010, work shifted from the initial compiler, that Rust compiler that was written in OCaml programming language, to self-hosted compiler based on LLVM written in Rust. And the compiler basically compiled itself in 2011. So this puts Rust as kind of 13 years old, and it's a relatively recent, it's a relatively young programming language, and it's a bit late to the game. Kind of like Kaspa in a grand scheme of things. Being late gives one advantage, as one can learn from mistakes of others and avoiding them, as well as to capitalize on the things that have proven to work. So Kaspa has only been around a couple of years, but as some of you may know, if you're following Kaspa, let's say Ethereum has something known as an uncle block, and this is kind of partial application of the ghost tag algorithm that was created by Jonathan and Aviv. So this is effectively the initial of Kaspa. Kaspa really has its origins from the academic community, and because Jonathan, Aviv, and a lot of people involved in the project are academics, and this is basically, a difference between doing a research and making a project, making an actual functional software. So it took them a little while, but eventually they managed to get that done, and now we have a fully functional L1 that's stable and operates for a number of years, and getting a couple of really amazing upgrades in the coming months. So, and just the same, it basically the whole ethos of Rust, the developers who were developing in C++ and have many years of experience, they when they started working on Rust, they took a step back and they kind of said amongst themselves, what are all the problems that we are experiencing right now as software developers using C++ and other programming languages, and what can we do to fix them? And a lot of Rust is based in that kind of mentality. Its origins come from basically that kind of point of view. One of my kind of favorite part of the Rust history is that in Mozilla San Francisco office, somebody put a piece of paper very high on the wall, saying that you must be that tall to write multi-threaded code. Basically signifying that you really need to be experienced and understanding how everything works with multi-threading in order to be able to create stable, reliable multi-threaded code. It's a very big problem. If you start with C++ and you start developing multi-threaded code, you will very quickly be exposed to a variety of conditions and circumstances where you will run into problems and you will need to mitigate them, because multi-threaded code runs in parallel, and that can create a variety of problems like race conditions, so on and so forth. And Rust, through its basically technology or through its programming language solves a lot of these problems. So from the project management standpoint, and this is very important, what does Rust offer? Like, why would, if you are not even a, if you're not a developer, or if you're a developer, why would you adopt Rust? And this is my personal view on my personal experience of working with Rust. So first of all, it's a commonly known thing, which is software reliability. Software in Rust does not produce unexpected behavior. Effectively, whatever you code will work as designed. And this is, you could argue that behind other projects, but this is much deeper than that. Rust prevents, the way Rust is designed prevents a variety of circumstances from occurring within the application. Long-term sustainability. There's this kind of notion of ease of long-term code-based management in large projects. As I've mentioned, I've developed very large projects in C++ with teams of people, as well as in JavaScript and TypeScript. And what frequently happens as your code base grows, it becomes very, very large, comprised of many, many modules. It becomes really difficult to manage the code. You start to need to have a holistic understanding of a lot of this code, and it just becomes tough. And frequently, to mitigate that, you need to hire additional people to take care of different modules. With Rust, that whole paradigm gets much more delayed. Working on, let's say, Rusty Kaspa, which is a very large code base at this point, I'm able to go in and I'm able to do changes in specific areas and not be concerned about breaking the rest of the software sort of. Rust is excellent integrated documentation. Rust has this ability through bindings to target different, basically, compilation targets or platforms which are native, basically like regular desktop native CPU applications that run in the operating system. WebAssembly, you can export anything to Python, Dart, Swift, etc. There's a bunch of others. Equally, from the other side, if you have an existing C code, you can, or C++ code, you can bring it into Rust using an FFI, a foreign function interface bindings library, which is also excellent in Rust. So there's actually a lot of existing stable C++ libraries that have been ported into Rust as crates and are available. Rust also provides an excellent tool chain that includes a number of tools that effectively offer compiler guided development. First of all, Rust C teaches you, meaning that whenever you make a mistake, whenever you do something wrong in the code, the messages that come out, the errors that compiler generates, not only point out the error, but it also points out various solutions to the error. And in general, it's very easy to see what it is that you're doing wrong. There are tools like Cargo Check and a superset of that tool called Cargo Clippy, which do analysis of your code, and they do a variety of linting, which exists everywhere else, but they also do kind of compilation analysis and tell you where your code might not be optimal, where if you have, let's say, multiple conditions, they could be merged into one to make the code more optimal, and so on and so forth. Basically, tells you how to optimize your code right there and then during compilation. And then there is a tool called Rust Analyzer, which really is the backbone of development. It integrates into a variety of IDEs, and what it does is that it compiles Rust code base in the background. And as it compiles Rust code base in the background, combined with basically the IDE tells you what your errors are as you are coding. So you actually no longer need to compile. You just write the code, and the compiler is just in real time is telling you, oh, like you have to do this, and as you do this, oh well, here there's this missing, and it is providing guidance, which makes the flow like if you start writing a function, you have an idea of what the function is. You can just kind of close your eyes and follow what compiler is telling you. It will guide you through completing and fixing everything. So in Visual Studio, which is the IDE I use, I know there's different people use different IDEs, but similar tools are available. I want to point out four key extensions that I always talk about and on the Kaspa Discord, and always point them out to people, which is first the Rust Analyzer. It makes the compilation of code in the background, giving you real-time feedback from compiler. You don't need to compile. It just tells you what's going on. Second one is Error Lens. Error Lens is gives what that tool does. It's applicable to all languages, but it puts errors where the code is. So if you have a missing comma or a syntax error, it displays the error on the same line in the IDE, where you no longer need to look in the terminal or anywhere else. It effectively, as you type, it just says right next to it what you might be doing wrong. This accelerates the development greatly. There's an extension called Even Better TOML, which TOML is a kind of a standard de facto format, similar, like it's if somebody doesn't know, there's a JSON, there's YAML, there's TOML. These are all kind of standard data definition formats. And there is an extension called Dependy. Dependy analyzes your, it actually works again in multiple languages, including Node.js and such. It analyzes your dependencies, and it checks line against the latest versions and points out if any of your dependencies might be outdated. So these are the tools that basically I use every day as a Rust developer. And then there is, over the last couple of years, I'd say more over last year, AI came more to fruition, really matured. And one of the solutions that I've used is Tab9. I haven't used that recently. Then there is GitHub Copilot, and GitHub Copilot gives you auto-completion. Basically, it analyzes the code and makes suggestion what you intend to write. And it's really great, especially when you're doing kind of pattern-based things. You start writing something, it understands, and then it offers you to write more code for you, which I would say is maybe like 70-80% of success rate of me accepting its completions. And over the last couple of months, specifically, something came to fruition, a project called Cursor. Cursor is a fork of Visual Studio IDE. And it is the same as Visual Studio, but it offers you an additional panel with AI integrated in it. And you can use different AIs as backend. It can use OpenAI, ChatGPT, or it can use Claude. You can basically tell it what you would like it to do, and what you would like it to do, and it can write the code for you. two mainstream systems, two mainstream AI technologies that are OpenAI, ChatGPT, and Claude by Anthropic. Claude is vastly superior to OpenAI. Claude is maybe like a year behind on Rust, and if you give it correct instructions, it can do a lot of code for you. And what Cursor specifically allows is that if you have actual code, you can tell it to modify your code and like, I don't know, write a function that split this line by white space and it takes this variable. You can make it as complex as you want, and it will analyze the code and it will modify it, and Claude offers and Cursor offers that as effectively as effectively diff kind of user interface, which allows you to change that. AI, there's two sides to using AI in development. Basically, if you don't know the programming language, if you don't know what you're doing, you can dig your own grave. If you do know, this can really help and accelerate you because it can really help you understand, do a lot of kind of research for you. Like the other day, I was writing a bunch of macros and I needed to do a bunch of syntax processing. And that typically involves going into documentation or into source libraries and doing the research, understanding what syntax elements we need to use, so on and so forth, and then running this code. And that can easily be between 1 to 3, 4 hours. And instead, I just told Cursor, make it process that type of syntax structure, so on and so forth. And it knows about all these elements, so it just created this code for me. So that's really can be a time accelerator. Equally as dangerous if you don't know what you're doing, but if you do, it can really help. I also seen people create really amazing things just by using Claude without any type of understanding of programming, which is scary a little. Rust is an amazing, great ecosystem. When we started working with Michael Sutton, he referred to that as a magic wonderland. It's a huge collection of stable, reliable, well-documented solutions, especially those focused on algorithmic processing libraries. There's all sorts of networking, very high-performance networking. Axiom is capable, is very easy to use and can handle bench over 500,000 requests per second. There's cryptography, encryption, bindings, interoperability, high efficient algorithms, especially things like, let's say, log-free, high performance map implementations or cache mechanisms. There's a library called Mocha, for example, that's really easy to use and it provides automatic cache. There was this, was talking to Super Typo at some point a number of years ago before he has adopted Rust as a language, and he said, like, I don't remember what the conversation was about, but he kind of said, we need to use a map, and I'm going to go install Redis. And I said, why do you need to install Redis? Just instantiate the map in Rust or use Mocha, and you have all these capabilities such as HTTP servers, proxy, caching mechanisms, and such, all as libraries. And as libraries, not as isolated applications, you have much more precise control over these elements. You can configure and make them behave and function however you want. So, due to its stability and variety of features, Rust is also the default go-to cryptocurrency for cryptography projects, as well as a variety of cryptography libraries are available in Rust uh, and maintained in Rust. But that also has to do with memory safety. Rust has a number of features that make it very difficult for um, to make mistakes or do memory overrides, which are the sort of the leading cause of various vulnerabilities and basically security vulnerabilities that are constantly hitting us from different directions in a classic code written in C, C++, and such. So, diving slightly into Rust internals. And so this list of Rust internals is really just a set of things that I wanted to talk about because I think that they play, it's not by any means a holistic overview or a tutorial on Rust or anything like this. Just these specific elements are key elements that facilitate variety of stability and features in our in Kaspa SDK and play into the overall SDK design and how we do some of these things. It's nothing. If you're very familiar with Rust, this won't be interesting to you. If you are learning Rust or you're using Rust only for a couple of months or a year or want to adopt, you should pay attention to these elements because um, they play a significant role. So enums in any programming language are enumerations. They are just a collection of basically values, but in Rust, collections of variants. But in Rust, these variants can also carry data like structs, and which makes the pattern of working with enums very pleasant and very useful because depending on the type of the variant, you can supply different type of data. Uh, I have added variety of to whoever is recording kind of key points, but I'm not going to be covering them. Just go over kind of general overview, and you can, if you have access to the slides, you can then read that on your own or the video pause and just take a look at that. So enums, it's not about as much enums as it is about the match statement. The match statement does not to have missing variant cases. Basically, if your enum has a number of variants and you do a match and you're missing a variant, the language will tell you about that you're missing that specific variant. You can forcefully skip it, but it's generally a bad thing to do because one of the things that happens, which I find really, really useful, is if you have an enum in a large project, let's say in Kaspa, and let's say in RPC or some other elements, and I add a new enum variant for custom behavior, what happens is all the match statements that are uh, checking this enum, they will immediately error throughout the entire project, telling you immediately where the logic is missing, where you need to update the match and you need to handle these specific cases. This is extremely useful in certain ways, in certain cases. One of the kind of core pillars of Rust is also conditional compilation. Uh, which are called CFG. So in the Kaspa team, we kind of call them gates. They allow you to compile Rust, compile different parts of the Rust code targeted to different platform. And you have similar things available in other programming languages, like the macros in C++. But this is much more elegant in Rust. And one of the things that we use this everywhere is you can have the same basically function that is named the same and has the same signature compile one function that is not named the same compile from one platform, but this is basically a function that is named the same but has a different body and implementation compiled for another platform. And then you have effectively a function that has different internals, but it depending on which platform is targeted, the function, different function gets executed. So it kind of creates an abstraction for the functions and various other internal elements. Borrow checker is another. It's an important thing to note. Borrow checker is what a lot of newcomers have trouble with. It is something that is integral to Rust and is a part of the Rust ownership model. But effectively, borrow checker is the way to access the variables and data in your application. That is that allows for the ownership of this data or access to it, facilitating basically memory safety and ability to track data existence without needing the garbage collection. I'm going to skip getting into this details. You can look this up online. These are common ones. Sense of null. This is another pretty big element within the Rust. Does not have such a concept as a null point or null value. Rust instead has, for example, an option type, and an option type is an enum which can have two variants: a sum containing a value or none. And so, whenever you want to produce some sort of result or check something, you're dealing with an enum which explicitly requires you to handle either sum that contains the value versus none, which does not contain the value. This is very different than in when you're dealing with like null pointers and things like that. Because you can have unexpected null pointers. You can effectively somebody could be returning you information, but suddenly it will be nullified. You don't know if you need to check if it's null, and you can run into problems with that. Explicit mutability is another very helpful feature. All the data in Rust is read-only unless explicitly specified to be mutable. So you cannot accidentally modify mutable variables. It helps you really keep track of variables that needs to be changed, and you cannot accidentally affect those variables that cannot be changed. Obviously, strict type system in Rust is very powerful because it prevents errors at compile. And second, key point that I'm trying to to highlight. A trait-based inheritance is also very different. This is very different from object-oriented pattern, where you have some kind of data associated associated functions. The traits in Rust can be associated with any object, so they allow you to create shared behavior. And there's also generics, which I'm not going to get into, but they can be traded. So you can receive a generic, and you just say that whatever the generic that I'm receiving, I want to make sure that it has a specific trait, and then trait defines functions. So what will happen is that if you try to pass this function or utilize some struct or something that does not have this trait, the compiler will refuse to use that. Otherwise, uh, it will accept that, and within the function that receives this generic, you can assume that the trait is there, and you can use all the functions that are present on this trait. Asynchronous Rust. Asynchronous Rust is very similar to JavaScript async in terms of its usage. It provides ability to do concurrency without multi-threading. It's effectively um, a task-driven model that can provide you multitasking, basically kind of a non-preemptive multitasking, but on a single thread if needed, or in a multi-threaded environment. And there's a whole bunch of benefits of using async Rust. The one of the, and we're slowly starting to get closer to the SDK. One of the key elements of async Rust is that when you operate in WASM, in a WebAssembly browser environment, using async Rust is really helpful, because similarly to JavaScript, it provides the environment where you can have concurrent execution, because browsers are single threaded, and so that means that if you create any kind of long running task, it will block the browser, it will block the web application. Whereas async Rust allows to basically go around that. So I jump forward. There is actually one of the sort of hacks that we have been doing in async Rust in the browser, which is using a application like using a function called yield executor to Junie. Junie, did you just turn up the microphone? That doesn't happen. If you bring it down, because making a lot of music is not a solution to that. Yeah, that's probably fine. Yeah, that's fine. Thank you. So we have a function called yield executor, which in the background actually calls a request animation frame, which can provide additional relief to the actual browser. So even if we have a code that, let's say, does some kind of cryptography related function, and it needs to do a lot of processing, your application can hang. Doing basically this type of approach can relieve some of the burden. Same kind of way sometimes you do that in a JavaScript universe. Another key one of the basically features or techniques that are used in Rust. They're called channels. And channels are really great because they are basically very thread friendly, and they allow very easy to communicate data across threads or across tasks. Effectively, you just push data on it, and then regardless from which thread, you can pull this data from it. So there's a bunch of ecosystems and tools that revolve around that, and make it really, really easy to share data between threads, because otherwise they basically do all the complex data protection and sharing very, very easy in Rust. There's another tool that deserves mention. If you don't know, it's called Rayon. Rayon is basically a multi-threaded library, and it uses regular iterators that can execute in parallel. So effectively, if you were to write a regular idiomatic Rust code where you get a series of data that you want to process, you will do that linearly by iterating over this data. The same with Rayon, what you can do is you can chunk this data, and you can just kind of give it to Rayon and say, I want every act to be multiplied or on 5 or somehow mutated, but I want this to be parallelized, and it will automatically handle the parallelization for you and deliver, and then basically it will chunk the data into different chunks, get different threads to execute that, and then reassemble the data, delivering it back to you without you needing to worry about that. There's a number, like in Rusty Kaspa core, in the core consensus engine, there is a number of algorithms that use Rayon to really accelerate processing. I think some transaction processing uses that, and in general, this is a very useful tool to use. So now we are coming to the to basically what I consider my most favorite part of Rust, which is macros. And in Rust, there is a few types of macros. There are declarative macros. Declarative macros are reminiscent of macros in other languages. It's a custom syntax that allows you to declare a macro and then repeat, basically utilize this macro to create a repeating code that maybe has some logic, but basically it's, let's say, similar to the way you would create a macro in C++ or something like that using template engine. Then there are something called derived macros. We'll get shortly into proc macros. The interesting part about derived macros and the proc macros is that if you remember during the introduction to the Rust programming language, I mentioned that they have initially written the Rust C compiler in OCaml, and then they rewrote the Rust C compiler to compile using Rust C. It compiles itself, which means that in Rust, you have access to crates and tools which expose the compiler functionality. That means that you can easily create any program that, let's say, parses Rust code, does any kind of analysis, does syntax parsing, or anything like this. What basically the proc macro clusters of macros in Rust are unique, on my view, in that what they allow you to do is they are like they're programs, effectively like plugins that get compiled by the Rust C compiler before the program gets compiled. They're the first thing to compile, and then these macros are loaded in the compiler like plugins when you compile your application. So effectively, to make a macro, what you do is you write your own Rust code that receives any syntax and then outputs any syntax on the output. So an example of basically allowing you to make a macro that parses the part of the of your own application and rewrites your code during the compilation using Rust programming language. So we have this macro called describe, and in the source code we're defining this in this example. In the source code, we're deriving a method called describe. We are saying we have. So this is from one of the Kaspa applications called Keynote. Then we have another attribute that we specify, and then the enum value. And this syntax that we write here is loaded into the macro processor, and the macro processor then, which is your Rust application, and it generates different Rust on the output. And then it generates this, let's say, there's a function called caption, which is where the value is extracted from this attribute caption. It implements an iterator, which can process all the variants. Then there is a function describe, which extracts the information from describe attribute, and Rust, which extracts the information from the documentation elements. So the most common or one of the simplest examples would be a derived macro called debug. What the derived macro debug does is that it you put it above the struct, and that happens with every derived macro. But in the debug example, you put it above the struct, and the struct has a bunch of fields. So this is then passed to the macro. The macro receives this struct as abstract syntax tree. It's effectively already parsed compiler data. It then analyzes every field in the enum, and for every field, it then creates a function called debug, and inside of this function, it logs each of these fields. So by simply tagging something with debug in the derived macro, you automatically get this function created and appended to your struct that is called debug, that you can call, and it will log all the values of your struct at any point. And this is extremely powerful way of analyzing and doing customization of any struct processing, anything like that, effectively. Then there are attribute macros. So the derived macros that I just described, the key element about derived macros is that they can receive struct or any data, but they cannot this. This data is read only for them. They can only create things after this data, such as implement traits, fix different functions and such, but they cannot touch the original data. The attribute macros, on the other side, they like derived macros, they receive the underlying code, but what they can then do is they can also modify the underlying code. They can completely change the code behavior internally. And attribute macros can be affixed to structures where they can rewrite or modify structures in a variety of ways. They also, like in the case of WASM bindgen, which is WebAssembly bindgen macro, the what this macro attribute does is that it first what it is attached to. Is it a struct? Is it an impl block? And then depending on the type of code it is attached to, it performs different actions. So if and in Rust, an impl block basically contains function definitions, implementations. So when WASM is attached to an impl block, what it will do is it will analyze every it will analyze action in the impl block, and it will create WASM bindings. Basically, it will create a needed instrumentation to expose these functions to WebAssembly, to make them available in TypeScript and JavaScript, effectively, completely automating the process. And here is, for example, then the fix to something. The last variant that exists are just raw proc macros. Proc macros, they don't need to affix to anything. You just declare them anywhere, and they function on input. You pass them something, and they then iterate on the information that you passed, and they generate Rust code on the output based on the information that you passed. So perfect example for that is actually Rusty Kaspa-RPC. This is used in a variety of places. This is used in WASM bindings, in WRPC client. Effectively, what we have as for every RPC call, there is a standard methodology, a standard function that needs to operate the same way, but on different data structures. Basically, you have a request and response data structure that need to be serialized, need to be dealt with, and but the function is the same. So what we have this macro called build WRPC client interface. And we basically fix it. The key element is that we pass it different enum variants, basically RPC methods such as ping, add peer, get block, etc. And what so the market receives this information, these tokens, and then what it does is that it takes the token, let's say ping, and it create internally, because it has access to that as syntax, it creates such names as ping request, ping response, ping call as a function body, and as well as the body of the function itself. Basically there is identifier manipulation that occurs and snake conversion. And then for every item, once it has created these, it creates Rust functions, which is what I just mentioned, ping call, and we can see with ping call that it has ping request that receives a ping result, and so on and so forth. So creating these functions manually is basically impossible. It's a maintenance nightmare. But automating them through macro, where you just give it the name of the RPC method, and then the functionality is created for you automatically at compilation time, is really makes things very easy. And what's also interesting is because this is the way this works is that um, uh, when you are building the input for macros, um, the linkage between the identifiers and types remains live. What that means is that if you, let's say, you have a data structure, you specify data structure in the macro, you can click on it or hit F12 in Visual Studio and navigate to the definition of that. So this thing, basically, the key point, about these techniques and tools is that make it really they make it really easy and efficient for us to manage a very large chunks of code base um, by easy means. So um, when we started developing the WebAssembly bindings, uh, we spent a couple of months working and made the first release, and we ran into a serious problem that required us to re-engineer everything from ground up. And this was actually something kind of obvious, but I did not realize that at the time. We initially took Rusty Kaspa internally is a very, very high performance data processing engine. And when so all the data structures that are used in this engine are basic data structures. They contain fields, they contain data, and there's basically a processing flow. The data gets created, it gets processed, maybe it's cached somewhere, but eventually it's thrown out, it's stored to the database, and it's thrown out. So we took these data structures and we exposed them to WebAssembly. But the interesting thing about there is a notion of a Rust ownership, where you have to own the data that you're dealing with. So when you deal with bindings like WebAssembly, let's say this means JavaScript, you can create a function that, let's say, returns a struct to JavaScript, and you get automatic scaffolding. You get everything is done by WASM BindGen. You just take a structure from Rust and you return it. You return the value to the JavaScript. JavaScript gets a structure. Everything is good. Everybody is happy. But what happens with the structure is that when you return it to JavaScript. Means that Rust gives up the ownership. So effectively, you pass it out and you forget about it. So one of the problems that we sort of ran in, if you have a nested structure, let's say you have a struct A, which owns a variable B of type of struct B, which owns a variable C of type of C, and then you have inside of C, you have a value. And then in JavaScript, you declare you have class A, B, and C that has a value. And then you create the A, and obviously A owns B that owns C that has a value. And you use the basically an accessor, getter setter, ABC value equals 42. And then you check it, and suddenly the value is 0. Why is the value 0? Is because when you do a dot B, you get a clone of B. when you do B.C, you get a clone of B of C. So you're getting copies of these objects, not some type of references to them. As a result, you are setting value to 42 on C, but that C does no longer exist in Rust. It returns these full objects. Uh, to mitigate that, we had to basically we had to resort to uh, with structures that are uh, basically we replicate the JavaScript model, sort of, where we have when we clone the structure, we get um, we get uh, the inner part of the structure is reference counted. Basically, multiple clones of the same structure refer to the same internals. So now, if we have in this example impl A, the A owns the B, but B is within the reference count within the mutex. So if you if you basically export the B, it makes it the copy of the the copy of the B will be referencing the same data. Will be pointing to the same data in web in Rust. So at this point, if you have in JavaScript, you do ABC, value equals 42, then you're able to assign the value to that. I have to apologize a bit. It's a bit difficult for me to speak because of the music, and in general, it's actually very makes it difficult to concentrate in general. So I'm doing my best here, but uh, because of this, we we have with basically a dual layer system in the Kaspa framework. Effectively, for all core primitive data structures such as transaction, input, output, and such, we have the structures that are defined inside of census layer, uh, processing, similar structures, identical structures defined in the what's known as a client layer, where you are able to use the structures to expose them to WebAssembly, to expose them through different bindings while retaining referencing same objects effectively. Uh, so now there's different ways to handle in the the question is what can mutex and not something else. Um, we are forced to use a sync Rust. Basically, when we write the code, it pretty much always needs to be async for it to be easily used in the browser environment without any blocking. But the same code needs to run on a native platform, and on a native platform, there's different there's something in Rust as executors. Executors is effectively an engine that facilitates execution of asynchronous code. So it's kind of it's a future poller that executes async code. So effectively, in the browser, there is a in the browser there is its own executor that's provided by WASM Bindgen. There's a bunch of libraries that have different executors, and on the native platform, one of the most common executors that is used is Tokyo. Stands for Token IO. And what happens is that we write the same code, but we are using the macro to make this code function in a native platform under Tokyo or browser environment under WASM Bindgen executor. Um, this code needs to function everywhere, but the way you spawn asynchronous tasks is different. So we use the previously mentioned conditional compilation macros to define similar functions, such as spawn, where when you build for native, it becomes a Tokyo spawn. But when you build for WebAssembly, it becomes a different spawn that is meant to be for web assembly. The problem is that they have different requirements. The Tokyo requires the code to be basically thread safe, while the browser actually does not require the code to be thread safe because it's a single threaded environment, different limitation. So there is something that is in Rust that is called send and sync, and these are basically markers that can be put on any structures or traits to indicate whether this structure is expecting to deal with thread safe information, or it does not need to deal with thread safe information. Effectively, send allows for something to be a send marker means that some data can move between the threads, and that also means that if you have an async code, it can be moved between the tasks. If the data does not have this send capability, Rust compiler will prevent you, it will not allow you to migrate this data between the threads, basically cutting off this ability at the compilation time, which is very valuable because there's no such limitations, once again, in something like C, C++, and you can have something that is not thread safe, you pass it to another thread, and so sooner than later, you'll have a variety of problems. And sync is something that allows data to be basically to have shared references between threads of the same data. One of the basically examples, there are two primary reference counters in Rust, which are known as ARC and RC, which is RC stands for reference count, and ARC is asynchronous reference count. This is very similar to what's known in C++ as smart pointers. It's when you have one data, but you can create smart pointers to it. And when smart pointers are no longer present, when the counter to references goes down to 0, the data in the smart pointer is deleted. So the interesting thing about RC and ARC is that RC uses to implement reference counting. RC uses regular integers, regular variables. So it increments the variable and decrements it. But this is not a thread safe way of doing this. In order to have a thread safe increment or decrement, you need to utilize atomic types. So this is why Well, I think it's. I said yeah. I said asynchronous reference count. It's atomic reference count, which means that the actual counter inside it uses atomic variables, which are thread safe. Atomics are there's different implementations about atomics, but generally speaking, there are specific CPU instructions in the CPU that guarantee that they cannot have concurrent, basically, read and write by the CPU when there's multiple CPU cores accessing the data. They are thread safe for data exchange. It's a bit of a complex topic, but the interesting thing about the send and sync macros is that send and sync markers, which are kind of like trades. In fact, I think they're trades. They're just kind of named slightly different, and are a part of the Rust programming language internals. What RC does is if you use any variable containing any structure containing RC data type, it has a marker inversion. It basically, if you typically indicate that something is a send or sync compatible, you will say send or sync. But what RC does is that it specifies as not send. It's an exclamation mark send. And what that does is that if you try to use this data type inside of any data structure, it poisons this data structure, basically cascading this not send definition all the way to the top of whoever owns this data structure, is basically indicating that, hey, this data structure is no longer thread safe. And the data structure owning it is no longer thread safe. The data structure owning it is no longer thread safe. So you have a thread safe code, you stick somewhere RC, and suddenly your entire application fails to compile because there's something in it that is no longer thread safe. So this is basically the summary of what I was kind of talking about, where we have a spawn function, and the variable a in this the variable a needs to be sent in order to pass it to the async closure that is being basically a task that is being spawned here. In JavaScript in the browser, it does not need to be sent because it's a single threaded environment. So we, however, if we're writing code that functions in all these environments, we have to kind of take the most restrictive one. We have to make sure that it is sent even in the browser. So it's a little, it feels counterintuitive in the beginning, but we end up writing the code that is thread safe in a browser that does not require thread safe. But there are basically, other than syntactic sugar, there are no penalties that revolve around that. This does not introduce any penalties. A mutex is sort of a bypass; it doesn't really do anything. But what that does allow to do is for your code to run in all different in WASM 32 and native. So that was one of the sort of challenges. So we went over. I basically, to do a quick recap. I went over macros. We use macros a lot to facilitate code automation. I went over the whole basically need to use thread safety within the code that even operates in WASM 32. Then there is another sort of issue that gradually creeped up as we were building the SDK. Any Rust structure which is represented in Rust, it can be exposed to WebAssembly, to JavaScript, and accessible to JavaScript. And then you can effectively expose any of its properties to JavaScript and such. And we were exposing properties, but these are they're exposed to the getters, and they're kind of they can represent the object. It's a kind of a free for all interface. You can do whatever you want with them. But what we quickly learned that a JavaScript developer who is using that expect that this that thinks that these properties actually represent the actual object type. But the reality is that object is hidden in the Rust, the WASP32 runtime inside of Rust. So what we sort of had to first do is make sure that before we were doing kind of we're taking more relaxed what we exposed to WASP. We had to constrict and make this data that we exposed to WASP more basically resemble what you would get as a JavaScript object, effectively mirror the Rust object through these getters in JavaScript kind of one-to-one. And then the next thing that started happening is because people see that you have a developers see that you have an object and this object has properties. What they do is they construct a regular JavaScript object and they pass it to a Rust function. But the Rust function expects a Rust type, it expects a Rust object. So it cannot just accept random object. So what to do, basically, how to handle that effectively? In this example, I have two different objects. So the first one is x and this x1, and then there is x2, and x2 is a pure JavaScript object. And then you want to have a function called do something, and you want it to receive x1 or you want it to receive x2. At that, if the x1 in x1 example where we're using a type x declared in Rust, you want it to pick up the Rust object. You don't want to process these getters and the fields from JavaScript. Whereas you also want it to accept the x2, which is the pure JavaScript object not associated with Rust. So to facilitate that, we have created a special set of tools and a trait called try cast from JS. And this trait, it has this function, basically resolve cast, which receives the value and then it receives a closure. Closure is like a callback in JavaScript. And basically, what happens here is that this function receives the value and it tries to analyze if this is a Rust data type. If this is a Rust data type, it then processes and gives you this Rust data type. If it is not, it tries to latch onto it as a regular JavaScript object, and it starts extracting the properties from this JavaScript object to try to basically assemble that. If something is missing, it will error out. Otherwise, it will read a raw JavaScript object and construct the Rust data type that Rust can deal with. So effectively, if a value is a Rust data type, you will immediately get a transaction input. Otherwise, it will see if this is an object, and if it is, it will try to read out all the properties from this object that belong to transaction input and create that for you on the fly. Utilizing Rust is on the Rust native types everywhere is faster because there's no additional processing overhead. But there are kind of really no difference in terms of performance and such. And uh, I'd like to kind of use to facilitate all that handling on the Rust side, which is WASM BindGen, WebSys, and GSSys. WASM BindGen provides binding automation. If you have Rust functions, you just attach WASM BindGen macro to it, and these functions or property or structs and such become available in JavaScript, TypeScript immediately. If so, when you deal with JavaScript, however, there is a variety of JavaScript data types, such as JavaScript object, array, number, map, native JavaScript data types. The GSSys provides the functionality to deal with that. And then there is a very large automatically generated WebSys crate, because what I have mentioned so far is using WASM BindGen to export your program functions into JavaScript. But you can also use WASM BindGen to bring your to bring any JavaScript function into Rust to make it callable and available in Rust. So what WebSys does is that it uses WASM BindGen plus a whole bunch of automation. It's actually, this crate is largely automatically generated, and it takes the entire browser JavaScript data, all the data structures, all the functions available in the browser that everyday JavaScript, TypeScript developer uses. And it makes these functions available in Rust. So you can write Rust code and have full access to the entire, basically, DOM management API, any Node.js functions. You can simply make a function in JavaScript, then declare it in Rust and use it from Rust. You can make a function in Rust, declare it through WASM BindGen, and use it in JavaScript. It's a two-way road, free for all. So now, given these basic primitives, there is something that which is called Workflow RS. Workflow originally it's part of another project. It really gained a lot of its maturity by being used in Rusty Kaspa. Original kind of the adventure sort of started when I tried to use. There's this wonderful environment where you can have a Rust code, and this code can run on a native platform or in the web browser. But there's no ability to communicate. You don't have any kind of network stack, and you kind of need at least. There's HTTP requests, but you really need to have kind of TCP stack, and the browser doesn't have anything other than WebSocket. So the WebSockets become the lowest common denominator, and basically, so WebSys previously mentioned, it offers access to W3C WebSocket class, basically the WebSocket available in the browser. And then in the native ecosystem of Rust, there's a crate called Tungstenite, which offers very good WebSocket implementation. So you have this native WebSocket, and you have this really clumsy browser WebSocket. So what I work on is a kind of WebSocket abstraction implementation where you have a WebSocket and you can interact with it in a uniform manner. But in the background, there is, if it's compiled for native, it will utilize tungstenite. And if it's compiled in a web assembly, it will utilize the browser WebSocket implementation. But this abstraction functions the same way everywhere using combination of basically macros and platform targeted code. So what what that provided us is the ability to have a WebSocket that kind of functions everywhere. This WebSocket functions in regular REST applications. It functions in the web browser, web extensions, any environment that implements WebSocket Plus, which includes things like Run, Dino, JavaScript environments, and one exception was Node.js. Luckily, there's an NPM module from Node.js that provides implementation of W3C WebSocket. So simply loading this module and making it available provides access to the WebSocket. So WorkflowRS has a couple of other components to it. Yeah, as I mentioned previously, we use async Rust, so it has a custom spawn function, which is different depending on the compilation target. It also has sleep intervals and timeouts, and that also is different depending on the compilation target. But these are abstractions, means that they have same signatures, they behave the same way on when you use them, their internals are different on different compilation targets. There is a special, so in web applications, there is in JavaScript, there is the only timing facilities are available are set timeout and set interval. And the interesting thing with the browser is that if the tab goes in the background, the browser puts the tab to sleep in order to economize process, basically resources of the computer. So when the tab goes to sleep, part of the things that the browser does, it suspends the functionality of set timeout and set interval. They simply stop working. The one bypass for that is to create a background, a web worker in the background, and have this web worker send messages to the tab, to your web application. The web worker in the background never goes to sleep. So this is an artificial way, bypass, to keep kind of the tab alive. So we have in Rust basically an automation that creates a background worker and does that. Directory access, couple of things like that. There is some platform neutral logging and some 32 utilities. There is serialization utilities, which are work in tandem with and are based on binary serialization called Borscht in Rust. There's a number of serializations. This is one of the kind of simplistic and most high performance serialization where it simply writes memory from values into a memory buffer, a vector of bytes, and then can deserialize by reading them. There's no processing required as long as you're serializing and deserializing the same structure. It is extremely efficient. There is some utilities for DOM manipulation, which flow into security slightly because one of the things that you can do with that is you can load if you have an existing JavaScript like we have there's a library called Xterm.js that we embed into Rust code, and then this library can be loaded from Rust, but it's loaded in a blob in a browser, and then nothing can access it. Whatever gets loaded in the blob is not accessible from the browser. I've spoken about workflow WebSocket. I guess I jumped in front on that page. Yeah, I wanted to say it's fascinating how months and months of actual work of getting this done can be reduced to a single presentation slide. And then what we have on top of this workflow WebSocket is workflow RPC. And an RPC is really a sort of simple scaffolding mechanism constructed on top of all the things that I have just described, starting with the WebSocket that basically does serialization of data, sends it over the WebSocket, and then receives the data, deserializes this, and basically functions as a very simple RPC using Rust functions. The data format for that is very similar to JSON RPC. The only difference is that this is getting delivered to over WebSocket. And there are two types of encoding. I mentioned Borscht earlier, which is a very high performance binary serialization. So that thing really basically takes the data structure, dumps it in a memory buffer, and ships it very quickly over the WebSocket. But the other encoding is JSON, which uses asserted JSON crate. And the difference here is that it takes the structure, serializes it as JSON, and then ships it over as JSON, as a JSON string. And if you actually look at the JSON payload and data exchange, it is almost one. It is like 99% the same as JSON RPC. There's one exception with regards to notifications and ID processing, where JSON RPC kind of has a shortcoming in its spec. So the one of the key elements of the workflow RPC is really that it's meant to be more of like an IPC, not an RPC. There's no additional work needs to be done to call function with arguments. You kind of you want the function to look and feel as if you're calling the function in another module. You don't want to feel that it exists in some other server, anything like this. And so that falls very well within the Kaspa internal RPC design, which is the RPC API trait. And RPC API trait is effectively a trait that has a bunch of functions representing RPC calls. So let's say earlier I was showing call ping. So ping call is the suffix, which receives the ping request and returns a ping result. And that's all that this trait does. It defines all these functions that have that have a suffix call, that basically RPC method name, suffix call, request structure, response structure. And the entire Kaspa RPC infrastructure is then modeled on this RPC trait, where it takes basically, if you need a server, basically you need to implement this RPC trait. So the client, let's say the WRPC client or gRPC client, it implements this trait. Implementing the trait means defining the bodies of this function, because the trait is kind of like a declarative declaration of these functions. So the client implements, the WRPC client implements connectivity functionality, the actual method invocation, everything needed to make this function operate, to make this trait operate and connect to a server. The server, on the other end, implements the same trait, but at this point, it's the other end. It's a server side of things. So this is it's if I do ping call on a client, I'm giving it maybe, let's say hypothetically, some data. It does something in the background, and then the function on the server called ping call gets called, and then the body of this function executes. The server return does some data processing, returns the result, and then comes back to this function. To you, this looks like function calls. And it's not a server; it's a peer-to-peer node. This is the Kaspa RPC, and the core trait, the main trait in Kaspa is RPC for services. The interesting part of the trait implementation is that it does not have to be an RPC. The one of the implementations that let's say Kaspa-NG has different ways of running Rusty Kaspa inside itself. Typically, it spawns Rusty Kaspa as a child process, a daemon, and manages this. But it can also spawn it as a thread. And when you spawn it as a thread, what you can get access to the RPC API trait, and then you can make calls directly to this trait without using any type of RPC. So this is this RPC API trait is this abstraction layer that allows that is implemented in the core of the node that received all RPC calls and responds to them, and then implemented within every client. And one of such clients is also WRPC client in WebAssembly, which simply takes Rust functions and exposes them to WebAssembly. So suddenly in TypeScript, JavaScript universe, you get all the same RPC functions, by calling which you're calling in reality Rust functions. Rust functions do serialization and communication with the node. Node response, the response goes to WebAssembly. And the same thing happens on Python. I haven't yet mentioned Python, but we have already working Python bindings that provide access to all RPC and most of the functionality. And the same thing happens there. The Rust functions are just exposed as Python functions. So you look at it, it smells like Python. You call a Python function, it returns you the value from RPC. But in reality, what happens is that this function in the background executes Rust code. So I mentioned the gRPC client is very similar to WRPC client. gRPC is the original protocol implemented by Rusty Kaspa in a Golang. It uses protocol definitions. And gRPC uses protobuf to serialize messages. Protobuf is one of the serialization formats. The trouble there sort of is that it creates an intermediary. There's basically two issues there. One, the protobuf format creates intermediary object representation. So the data arrives from gRPC, then it needs to be converted. The gRPC interface loads it into this intermediary representation, and then the intermediary representations get converted into Rusty Kaspa objects, native objects needed for RPC. So there's additional conversion layer. Another problem with the issue with gRPC, gRPC itself is very widely available. That's why it's going to continue being supported, and actively maintained because there's, almost every language has a client for it and such, but it still lacks a solid web infrastructure. If you have a web app in a web browser, you cannot connect to the gRPC client easily. So this is where having a WRPC and WebSocket really comes in handy, because this allows you to connect to the RPC endpoint from anywhere, including the web browser. So yeah, okay, I've managed that. It's interesting how I talk one slide up front. Another, so then there is effectively a Kaspa WRPC client that I mentioned. It effectively implements workflow RPC client implementation, and there is a server implementation in the node. And yeah, it implements this great called Kaspa WRPC client that is this multi-purpose kind of multi-platform client that functions everywhere. In addition to that, there is a separate application that was created a couple of months ago. This is called Kaspa Resolver. It's just it's kind of this basically cluster monitor application, high availability load balancer, if you use technical names for that. But what it really does is that if you have multiple nodes and they all have RPC interfaces, it connects to, or you specify for it to connect to all these different nodes. And then itself, it has an HTTP backend, HTTP front end, by which you can ask it to say, hey, give me the URL of one of these nodes that are live, and that have the least load, the least amount of connections. So Kaspa Resolver sits and monitors in real time all these nodes, monitors if they're in a sync state, monitors if the node has gone down. The second there's any trouble, it just removes the node from the pool of selection. Whenever you come to it with HTTP and you say, give me your best node, it runs elections based on the data it has and says, here's the node. One of the problems, there's basically two problems that have existed in the early days, where you have gRPC nodes, but you can run a public node on the open IP, but first you're susceptible to the DDoS attacks because anybody can hit your IP. And then it was kind of, oh, I'm running the node here, or this node is no longer working. And there's some people trying to run permanent nodes, but everything is very chaotic and kind of not really reliable, and every time you need to spin up the node. So the part of the effort to mitigate that was to have this to be able to run multiple nodes, have this Kaspa Resolver, but now through WRPC interface, not through gRPC, to monitor these nodes. And you just go to the resolver and you ask, give me something, and it gives you the best endpoint to the network. And I made during the KRC20 launch, we had over 20,000 wallets that powered up to utilize KRC tokens, and all the kind of servers that I had running nodes got completely overwhelmed by the socket demand. Everything completely malfunctioned. So that was the first kind of test run that Kasplex did. So we have, so I went back to the drawing board, updated Kaspa Resolver, and then did an outreach to the community, basically saying, everybody, we need to have we need to have more nodes, and we need to help the ecosystem provide the nodes for ecosystem to access. The this kind of infrastructure easily counters the decentralization. So all efforts have been made to make sure that this infrastructure remains decentralized. Nodes are operated by. We created this. We called this cluster public node network, PNN, and the nodes are operated by different contributors from around the world using different VPSs. Some are running nodes at home and such. We've created some tools. There's a tool called Keyhost that automates the deployment of the node, allowing everybody to upgrade or install them with ease. And then there's a whole bunch of basically DNS magic that happens in the background, where there's a number of community people who are trusted, who's been around for the last 2 years, that are supervising that infrastructure. The purpose of this infrastructure really, it kind of ended serving Kasplex, so serving wallets within the Kaspa ecosystem. You have developers, but developers who create an application, and then this application needs to have 10,000 endpoints, and the developer, let's say, is a contributor or a volunteer who basically who creates an application, but then cannot. He cannot afford to run 5 or 10 nodes. That ends up being costly to do. That can easily translate into a few $100s a month of VPS data center expenses and such. Providing these types of solutions with access to the network without having to run a local node and infrastructure from people who are contributors and participants who have access to the infrastructure, and kind of distributing the operational costs throughout the community, really helps facilitate that. And the most important thing, on my opinion, is that this infrastructure removes any friction from onboarding developers, because now anybody coming to Kaspa who wants to interface with Kaspa, test the SDK, access node APIs, or do anything like this, they just download the SDK, they run the application, it instantly connects to the node and gives them instant response, in basically instant information, or if you need to submit transaction, anything like this. It's if you are a serious entity, if you are a bank who wants to interface with Kaspa or something, by all means, you should be running your own node. If you simply running a node is very helpful. It contributes to the P2P ecosystem and decentralization. But this is this kind of analogous pathway that allows developers and newcomers and developers to quickly So now we're going to get into Rusty Kaspa. I have no idea how much I can talk for hours. I love this project, so it's really, wow. Need to hurry up. So the key logical components of the Rusty Kaspa framework. Basically, this is kind of my approximate layout of how the entire SDK is structured. We have framework primitives. And then we kind of have on one side of things, we have everything needed to run the node, the P2P node, the Rusty Kaspa itself. And on the left side, we have a variety of components that are meant to be shared between kind of the node and the client infrastructure. The census engine, bird's eye, kind of bird's eye view. This is I don't venture much into the consensus engine. I know all the components in there, but I don't really deal with them. I work on this left side of the previous graph mostly, but effectively there is when a node receives a block, it undergoes block acceptance validation. After which the block is goes into the block processing, and then basically the blocks is broken down into transactions, and there is transaction processing. The key element of this kind of bird's eye view diagram is to point out that there is many arrows going in parallel, and that these components are highly parallelized. This is from like I said, I've dealt with a lot of different applications in the past, but this is in terms of what Michael has designed. This is state of the art, multi-threaded, high performance data processor. It's really beautiful. So on the wallet SDK in Rusty Kaspa, there is a whole bunch of other components. Now, this is a client layer. This is what SDK, basically third-party developers, have access to when they want to build wallets or interact. A lot of this is also the heart of Kaspa-NG or the CLI wallet. But basically, from dealing with a lot of developers and integrations, I've seen that there is kind of two avenues people go with. Either they try to develop they try to deal with directly with the network and have their own UTXO, dealing with their own UTXO and transaction process and everything associated with it, or they adopt the framework infrastructure. Framework infrastructure is basically an integrated everything integrated wallet, and then integrated and then underlying components. So you can use wallet components, or you can use the entire wallet. So in terms of wallet components, there is you receive information from the node, and there's a main component called UTXO processor that manages event processing. Let's say new transactions coming in, and each UTXO processor can have UTXO contexts. UTXO context really is just a group of Kaspa addresses. So this is meant to serve as a set of account. Basically, each UTXO context is meant to be an account, but really you can give it any number of addresses to monitor for whatever purpose. You can instantiate as many UTXO context as you want. So in a context of an exchange, for example, if they're doing their own wallet, you will have one UTXO processor, and then each UTXO context would be a user. In a context of a user wallet, you would have one UTXO processor, which is once again a wallet, and then you would have a UTXO context as a, let's say, BIP44 account, basically a different wallet account. The service task provides this basically monitoring, and when because transactions come in and then they need to have certain amount of time to process confirmations. When this is called in the wallet SDK is maturity, when transaction is confirmed, otherwise known as mature, there are events that are coming in. So if somebody sends you Kaspa, so if you take this component, you add your address in here, you instantiate everything. There's a bunch of examples of using that. And then somebody sends you Kaspa. Then you just basically immediately, within a second, you will get an event saying that you have a pending transaction. And when the transaction is deemed confirmed, a few seconds later, you will get the transaction is confirmed. You can use the transaction immediately as well. You can use a pending UTXO. Basically, UTXO that comes in can be used immediately in Kaspa. The confirmation hold is artificial. We don't actually need to have the confirmation hold for regular transactions. It's kind of there for, I don't know, non-existing safety reasons in reality. But what can happen is that if there is any kind of double span attack or something goes wrong, you will have a cascading UTXO failure as a part of the reorg. So anyway, UTXO. So then there is another component which is called transaction generator, and transaction generator can you can take UTXO context and just give it to the transaction generator, or you can give transaction generator any number of UTXO entries that you've obtained from the node that belong to your wallet, and basically say, hey, create me a make me a transaction, and it creates the transaction for you. Now, what is the reason for transaction generator existence versus you simply making a simple transaction? The reason is that there are cases where you have too many UTXOs that cannot fit within a single transaction. If that case occurs, then transaction generator will create multiple basically chained transactions. They're not a chain, they're a tree, but it will create what's known as batch transactions. So here to just visually demonstrate the problem that occurs, as Maxim has mentioned in his presentation, in Kaspa there is a notion of mass, and there's a mass limit for a transaction. A mass limit of 100,000 grams in a single transaction. And let's assume that somebody sends you 100 transactions of one CAS, and you end up with 100 inputs. But if you want to generate a transaction, basically, if you take one output that needs to go out, and then you populate the rest of the transaction with inputs, you will hit the boundary of the mass limit at about 83 inputs and one output. So if you have 100 inputs, you cannot send them as you cannot send somebody 100 CAS because the transaction limit prevents that from happening. So what you need to do is you need to take this. You need to construct this transaction with 83 inputs, and then these 83 inputs, you have to send it to yourself, and then use that 83 this now becomes a single input 83 plus the remaining that you have, and you have a one transaction of 100 CAS. But while the output is 100 CAS, you had to execute two transactions to combine these UTXOs. There's different names over the years for that process. Basically, it's known as sweeping or batching or compounding. And there's different methodologies that are implemented for this. A number of wallets, like the wallet.kaspa.io, I think KSPR wallet, they are doing manual compounding enforcement. Manual compounding enforcement is where the wallet basically says, "Hey, you have too many UTXOs. You need to compound your transactions and it makes the user do that. The ultimate way is the transaction generator that is within the SDK. Transaction generator will handle this use case automatically. You tell it who you want to send funds, and if it encounters the condition of mass overflow, it will break it down. It will break the UTXOs down. But there are actually cases, especially with miners, because Kaspa is a very high performance system, and it's which means high frequency, which means that you can receive UTXOs very quickly over and over and over, and you can easily end up with hundreds or thousands of UTXOs, especially if they're like a relatively small and such. And so the what happens then, the way the generator will handle this, and I initially made a mistake. I made chain transactions, but then Michael has pointed out that this was a flaw in the way that this works. Is that if you have independent, basically independent UTXOs that you're consuming, and you're consuming them into independent transactions, that means that the independent means they're not related to each other. So if you have a bunch of UTXOs and you you compile them into one, creating another UTXO, and then basically transaction A does that, and transaction B does that. They because of the way the DAG is structured, that can happen absolutely in parallel. So as opposed to doing this sequentially, where you would compound, and let's say it costs you a certain amount of DAA scores. This is effectively the can be looked at as form of time in Kaspa. What happens with this transaction layout is that A and B will be executed simultaneously, and then the C can combine them. So in here, your transaction processing can be reduced by basically 1/3 if you, as opposed to you doing this sequentially. Um, so what I described right now is Wallet SDK, and then we also have something called Wallet API. A Wallet API is an actual implementation of the fully functional wallet within the Rusty Kaspa framework, and uh, it is available in uh, real, real, releases as the Kaspa wallet executable. This is the command line wallet. The same framework is also used in a number of other projects, including Kaspa NG. And what the basic elements of that framework is that it also has UTXO processor, which represents the wallet, and UTXO context counts, which are BIP32, BIP and BIP44 hierarchically deterministic accounts. You then, just like in the previous slide, transaction event generation. But with the wallet, you have serializable control interface. Effectively, it's an RPC-like trait on which you can make function calls to control the wallet. And then, in addition to that, this is what Wallet SDK does. But there is a transaction history and wallet storage. So the wallet storage, if it is in a browser, it uses local storage. If it is in, let's say, native and Node.js, it uses file.io. It stores it as a file. In Chrome extensions, it stores it using Chrome storage. And then transaction history is a bit of a problem in the web browser. Transaction history is stored in IndexedDB, which is a database. But otherwise, in native, transaction history is stored as separate files. And the reason that each transaction is stored as a file is because you don't really need that much high performance to access it. But what you do want is you want to be able to access the files from native Rust executable as well as Node.js, for example, or Bond or something like that. To load transaction history. So otherwise you have a breakage, like you can use a database in Node.js, but then you can't read it from Rust, so on and so forth. Uh, so uh, the way we handle documentation is that Rust documentation is documented in the source code and using Rust doc. And for 132, you compile to WebAssembly, as a part of which it generates JavaScript and TypeScript files, which contain all the Rust doc, but not projected onto JavaScript comments. And then you can run TypeDoc against that and gain JavaScript documentation for that. Some of the challenges that we have encountered, this is just a gift that keeps on giving, is what we refer to as TypeScript typings. When you build anything in Rust, everything is through its type system, everything is very solidly locked. But when you export these types to JavaScript or to TypeScript rather, everything is this relationships, they kind of get lost. So if you make a typo, if you incorrectly specify something, the only way to notice this is by testing that in the JavaScript TypeScript environment, which means that you would need to develop unit tests first of all on Rust, which there are, but also on JavaScript, which we there have been some attempts, but the SDK has been mutating a bit too much. It was a bit premature to do it. I think now it's the time that we can start automating tests in WASM 32 SDK. Like just a couple of days ago, it was pointed out by somebody that there was an incorrect name on the setter prefix. It was just accidentally named as something else, a typical typo that bypass. And until somebody uses that actual function, which this is like a very rare function to use, we can run into situations like this. Code review helps, but I have to say a big thanks to Captain PX because he's been as well as a couple of other developers very helpful at identifying these issues. Other challenges are to be done. Luckily, you can actually disable TypeScript type generation in WASM bindgen, and you can then declare your own in TypeScript. Work on these that is ongoing. The major key elements on the kind of SDK side and RPC side is RPC pagination. This is something that everybody in the core team has been avoiding to deal with. Basically, we have 1 gigabyte message limits, but in some conditions, it is possible to overflow that, and this is not web friendly. It's not friendly for WRPC, and we have been sort of working on. We actually have a design for kind of job-based control where you make a request and then you can get notifications, and you get a job ID, and then you can control the flow of data using that job. There's upcoming Python SDK release, which is very close. A couple of days ago, we've celebrated issuing a KRC 20 token using Python SDK, which is a major milestone in general. And this has been long coming. Again, CAF has taken the burden, but PSKT-WASM bindings are almost complete. When I'm going to be getting back home, we'll be reviewing that. So unfortunately, right now, we're kind of running out of time across the board, and this is not my laptop, but the Kaspa-NG is a good example of a secure and platform neutral application. It uses in Rust. It uses a user interface toolkit called EGUI or EGUI, and it's a wallet. It's a visualizer for the Kaspa network, and it runs on Windows, Linux, Mac OS, where it embeds Rusty Kaspa in it, and it can run this Rusty Kaspa. Basically, it's similar to Bitcoin Core desktop wallet. It can also run as a web application. If you go to http://kaspa-ng.org, you can access it and deal with it from the browser. It also can operate as a web extension, and it can also be started in the command line application. This is it on that. Let's. You have questions? No, because the way it's done is basically there are many nodes, there are many resolvers, and then there is many administrators, and it's a kind of a graph going down that starts with many nodes. Basically, there's a group of domain names that are owned by different parties. So, like if a car hits me tomorrow, the system will continue to operate without a problem. In fact, we had an outage, a bunch of nodes have gone down and such. There's been no issue whatsoever because they're just eliminated from the system and load is redistributed. But very like my my ethos is very Bitcoin focused. So I would not allow anything around me, around something like Kaspa, to have any kind of centralization elements. But it is also a very complex problem because you want to have basically a Web 2 infrastructure. You want to have web browsers to access something that looks like servers, and you want that to be decentralized. That's very actually a difficult problem to solve. So the way this has been addressed from the design standpoint is that you have again basically, let's say 32 nodes, and then you have let's say a whole bunch of resolvers. And each resolver connects to every node. So if resolver cuts out, when this functionality is integrated into WRPC, so when you connect to when you access the resolver, it knows about these 16 resolvers and it goes over them in a round robin fashion. So if a resolver is down, it will just jump to the next one. That's the only way to deal with that. But the second he finds a valid resolver, he will answer him, here's the node. So the resolution time is very quick. And then we have basically a whole kind of borrowed that from Cloudflare naming schema where there is short male and female names, and a small algorithm that mixes them up and generates them, and different administrators that own the domain names, and these domain names then. So if that domain name cuts off, there will be another group. So it does shift toward it does shift towards some centralized element, but it still is, on my opinion, centralized. It's redundant and resilient, which is another key element. And that's why I also pointed out is that if you are nothing prevents you from spinning up your own node and making the application interface against your node. In fact, when this case where I described when during the KRC-20 launch, we were overloaded. What happened is suddenly there was this huge inflow of KNG users, because you can download KNG, and these are not technical users, but you can download KNG, and then you can have your web wallet extension or web app connect to KNG to your local node. So there is basically there's a few, a big table of variety. I guess I'm trying to say what is a Swiss breakfast table of how you can configure, how you can connect and interface. But in the front end, in the SDK. So transaction generator is a queuing system, but it has a very complex algorithm that queues trees in order to parallelize the processing and make it as fast as possible. Then there's the whole subsystem of event processing, where you, for example, will be, if you just want to talk to the node, you will be receiving event notifications, such as you have a new UTXO, there is a reorg happened, basically listening to events to which you then, let's say a rudimentary wallet would basically power up, get a bunch of addresses, and then say to the node, I want to subscribe for any changes to these addresses for which you'll receive UTXO updates. And then you will go, okay, now I'm going to actually query you and tell me what are my UTXOs on these addresses, because there's two things. There's receive notifications, and there is what are my UTXOs, and you have to subscribe first and scan later, because actually a number of years ago when this was being designed, I ran into a problem head on, where I scan and then I subscribe. Meanwhile, UTXO comes in, and I miss it this way. So there's a particular sequence of that, and you would end up having a internal event processing loop to handle this. There's a bunch of examples on doing that in WASM, in Rust. That's on the client side. On the processing side, it's a huge, complex, multi-threaded data processing pipeline that is made out of not only multi-threaded modules, because we couple actually this part of the system that has strict classical strict threading model, where there is actually dedicated number of threads, like the block processor, which does processing in a strict controlled thread environment. So we have full explicit control of everything that's happening. That is then passes the data to to Tokyo, which is an async processor, which then does more fluid distribution using less resource. And in parallel, there is also during this processing, Rayon kicks in, let's say, to do some optimized multi-threaded processing on some of the data and such. And so uh, the engine, the P2P node engine 4 is one huge pipeline processor. Like, and the way I have this analogy, I wanted to do a slide, but I made too many slides now, is that if you look at the node, you would imagine a river or a waterfall. And if you look at the wallet, you would imagine a pond or a lake, because one takes in the data, does real-time processing, stores in the database, and eventually gets rid of the data. It's a real-time DAG processor. And then the other one is it aggregates UTXOs. It keeps them, maybe listens to a few drops of water coming in, but then at some point somebody opens a dump, it sends out some CAS, this kind of analogy. Right, we're way running over the time. Let's take a quick 10-minute break, and unfortunately, the most interesting parts are left for last. So 10 minutes, 4:40, we'll be back. All right, everybody, let's continue. I apologize for taking much more time. I should have. When we run scaling, we have the timing counter, and that allows you to track time, but I don't have one, so I completely overran the time. And well, let's hope this is that is useful to our Discord developer community and other developers. There is a lot of information, and I hope people do find time to watch it and to learn about it. So now we're gonna to cover the some of the elements. This is ongoing work that is taking place on the Kaspa, basically L1 smart contract. Testing 1, 2, 3. The things are going to start running out of battery at some point. So with regards to basically smart contracts on L1, the goal behind the effort is to make layer 1 Kaspa network compatible with the zero knowledge proofs, so that it can support development of effectively ZK rollup types of systems, effectively support layer 2 applications, or accept external data that is ZK provable. Obviously, the goal here also is to make the system make the network much more capable, and which will enhance the ecosystem functionality, and in turn will stimulate the proof of work ecosystem. And as we know, proof of work controls the security of the network. So this is very important. Another really important point to point out in the entire design approach of how smart contracts and basically how layer 1 Kaspa would handle any interfacing is that Kaspa as a network, as a software stack, aims to be L2 agnostic. Basically, there needs to be a neutrality and anybody is welcome to develop their own L2 systems so that execute their own smart contracts. So whatever. Our goal is to facilitate the of the stock at every basically at every level that we can in terms of a feature set and SDK and so on and so forth. So how does a bunch of fancy terms, ZK, so such? How do we achieve that? So first, we'll do a quick review of what is the ZK role. Basically, you can have a series of transactions on layer one. And they can be represented as block, but I chose to represent them as a series of transactions. And what happens on layer one, let's say Ethereum, a smart contract is basically asked to somehow instantiate a layer two kind of state. And what the smart contract on layer one will do on Ethereum, it will be asked to lock certain funds for use on the layer two. And these are known as wrapped funds, let's say wrapped Ethereum or something like this. But effectively, it freezes the funds, and it will not allow these funds to be spent. Meanwhile, on L2, these funds became available as this kind of virtual money, and L2 can process transactions using this virtual money. And at the end, the L2 has there's a set of balances that result of all of these transactions. So these balances that now these balances represent the originally locked balances in smart contracts. So these balances then need to be distributed the layer one. So the roll up effectively when this is done, it will construct the smart contract. There is a here are the new balances. And what it needs to do in addition to that, it needs to provide the a zero proof of all L2 execution to this smart contract, saying that, hey, here are the balances that please distribute that to different users, to different addresses, different tokens and such. And here's the proof that whatever happened in on L2 during this period between us getting these funds and distributing them, everything is true. Everything is provable. We'll get to that in a second. But effectively, these two components, once the smart contract receives that, he unlocks the funds and the funds are distributed. So the question is, to make smart contracts, you need smart contracts, because on Ethereum, smart contract. But on Kaspa, we don't really have smart contracts. So first of all, just kind of an overview of what is Kaspa. Kaspa is a state-of-the-art proof of work sequencer. Sorry, and I meant to say, and then soon to be a verifier, not a proofer. Ghost DAG algorithm determines consensus ordering. So you can kind of say that there's a bunch of transactions, and then you can prove something that has happened before. Quickly reviewing the what is a UTXO system. In a UTXO system, you have different blocks, blocks are comprised of transactions, and then effectively transactions are comprised of inputs and outputs, which can be represented as effectively UTXOs. UTXO is an unspent transaction, a transaction output, and then what UTXO from one output goes to can be consumed by the transaction in another output. So a little bit about Kaspa transaction processing. Kaspa transaction processing. The basically users submit transactions on the Kaspa network, and nodes rebroadcast these transactions, and basically each node receives all the broadcasted transactions, and they sit inside of something that is known as mempool. A mempool is a basically what the name says. It's a pool of transactions sitting in memory, and typically, like in Bitcoin, a mempool is ordered by priority fee. More expensive the transaction is, the higher the fee is in transaction, the the higher in the sort order they are, it will be consumed first. So then let's assume that we have two miners, miner A and miner B. They each want to mine a block. So they go to the mempool and they say, give me a bunch of, make me a block out of transactions. I want to give it to my miner to secure it, create proof of work for it. And I want to get involved in mining, participate this way. If miner A and miner B use classic schema like in Bitcoin, which is give me priority order transactions, they will result in exactly the same block. The block will be identical. So to mitigate that, the mempool selection actually uses weighted entropy. Basically, it's a fee rate based weighted random selection of transactions in the mempool. Which means that it is priority based, but every miner gets different variants of the transactions that he picks up. And as such, we can now see that in the diagram, miner A and miner B have resulted in two different blocks, block A and block B, and the block A and block B have some transactions are the same, but some transactions are unique. And this then goes into the DAG ordering algorithm, which is the consensus system, effectively, of Kaspa. The DAG ordering algorithm takes this block and takes these blocks and analyzes them and produces a deterministic result, which is a set of a unique set of transactions that exclude duplicates. And just a bit of terminology here. So here we have fee rate weighted random selection. Miners do proof of work, and then to some people who are new to Kaspa, there is terminology that is known as BPS, which is the blocks per second, and TPS, which is transactions per second. But note that this transactions per second metric actually includes transaction A twice because it is present in both blocks. So once this goes through deterministic transaction ordering and deduplication, the resulting transaction set is something that's known as effective TPS. That's eTPS. So if you run a Kaspa node and such, and you turn on performance metrics, you will see in these metrics BPS, TPS, but you will also see eTPS, that is the actual number of transactions that have passed through the system. So actually work. So transaction ordering, effectively, that last element here, A, B, C, X, Y, Z transactions, is something known that is a merge set. Um, so a merge set is basically blocks are laid out uh, in effectively time as an axis, but really it's for. And blocks also have relationships. Each block has a series of parents. And one of the things that the dot crossing algorithm does is that it basically a magic deterministic function that determines which block uh, s- uh, is selected to be is selected parent, which is how it's known, which is a selected parent. So, and the a chain of these blocks. These are known as this is known as a selected parent chain. So you can see here in the kind of green, block B has B apostrophe, which is selected of which the next block is, and the next block follows there. So this is selected parent chain. And the merge set, the rule for the merge set is as follow. This is all blocks within the past of the block B that are not within the past of the selected parent of B. So these guys are within the past of selected parent, but these guys are not. So all of these blocks basically that are tagged in yellow, including selected parent, all their transactions are collected, and all their transactions and a merge set of these transactions is created. So a merge set is basically now we're looking at a sequence of transactions that are deterministically ordered, basically resulting in a list of transactions. And the first element that we can introduce, sort of, with regards to the with regards to L2 and secondary layer interfacing, is that transactions can be transactions in Caspa have a subnet field, and the unique subnet field associated with transactions can basically can act as it's not a sharding mechanism, but it's effectively an isolation mechanism where you can, if an L2 is, for example, represented by a unique subnet identifier, you can now filter all the data delivery for that L2 that specifically belongs to that subnet identifier. This can optimize data processing in a variety of ways. So basically, another concept that needs to be introduced is basically UTXO state. UTXO in the UTXO system, basically the idea behind UTXO is that in addition to its usual data, it can actually have some additional auxiliary data in it. And this data, we can call it right now a state. A state can be, let's say, a hash or a Merkle root of some other data set. So it's effectively, if you now Save the day. All right, we're back. Actually, I actually like not having microphone. It's so. All right. So, so this the kind of bird's eye view of L1 and L2 interaction. The in L and transactions have a payload field. A payload is an arbitrary data buffer. It's a vector of bytes, and the payload is it can be anything. And currently in Kaspa, payload is disabled because we didn't want people to basically pollute the ecosystem without no reason or stress it in. Now with the Rusty Kaspa 1011 running stable for the Crescendo hard fork, which is the 10 BPS, 10 block per second hard fork that will be coming, the one of the considerations is to enable payload. We'll probably have some testnet mutations before that running with payloads actually fully loaded to stress test other elements of the node. Uh, so the payload can contain arbitrary data. So we're going to define two types of data, which is known as cold data and the ZK, and then ZK proofs. And effectively, what you can do here is to invoke a smart contract. You can send him different information and you basically arguments. You can think of a smart contract as a function, and this function takes a bunch of arguments. So call data represents these arguments as well as what a function that should be, which actual smart contract on L2 you want to invoke. As well as which states you want it to affect, and you basically you take this information in cold data and you send it to L2. L2 eventually says, "Hey, I'm offering you some proof." So if we put this in the context of the first diagram of ZK rollup, then we can look at it as let's say well yeah. So let's continue. I'm jumping too fast. So what do ZK rollups provide? The basically some of the elements they provide ability for a layer 2 to create transactions on layer 1. So if you have a provable code layer running on a layer 2, it can create a transaction on layer 1 that the layer 1 can accept. Basically, to transact CAS on layer 1 with instructions coming from layer 2. Basically, layer 2 can also post arbitrary data on layer one inside of transactions payloads. And when the transaction, because transactions on layer one are visible by everybody, or all L2s or all participants. So you can basically share arbitrary payload on to L1, and then such payload can, for example, be interpreted by another layer 2 network running against Kaspa, basically for interoperability purposes. So the thing that tools can do by creating proofs, it can proofs are is something that is easily basically very fast verifiable. So it can create effectively L2 can create commitments to its state. For example, if for example, well, in the case of jumping to the next point, in the case of peer-to-peer synchronization, for example, an L2 node can operate on its own, and then only when it receives the proof of its internal consistency, its internal basically state, it can only then data over peer to peer, which is that uh, if you if L2 execution as a smart contract platform, for example, is constantly proven, if all the state is proven. So I realize right now that I'm a bit skipping about the state. Basically, the you have two components. You have the program, and you have the state, the data. And the state is basically primarily represents the data that the program operates on. So when I'm referring to the state, that means that the program did something to the file, and and this file being an account, it did some modifications to that, and then basically we obtained a zero knowledge proof saying that this in fact did happen. The program has truthfully applied that element, or has done these changes to the data. So in the grand scheme of things, the layer 2 state proofing can also affect elements such as pruning, which is that when you have certain amount of time has passed, and there's a proof of all the changes that has been done on this specific state, the historical data can be deleted. In the case of Kaspa, pruning is achieved by cryptographic proofs. Effectively, as the data comes in, eventually only some of the data is kept that is cryptographically provable, and all the source block data that this cryptographically provable data originates from gets discarded. Unless you're running an archival node. An archival node will always catalog all the blocks and make all history available. So a similar element can be done with application can be done with ZK proofs. So L2 as a smart contract platform, its own performance considerations. Effectively, Kaspa is artificially constrained in its the whole like we don't have to the next upgrade doesn't have to be at 10 bps. It could be probably at 20 bps. The current performance engineering was done by the team. Uh, on my opinion, is sufficient enough that for it to kind of pull that data rate, even though I know that some might be skeptical because some algorithms have this rise in quadratic complexity when you're processing DAG. It's very complex engineering topics, but the reality is that it's artificially constrained. And the reason it's artificially constrained is for it to be able to run on commodity, on consumer hardware that anybody on their laptop can power up a node and utilize it. This is extremely an important component of decentralization. So what has been done sort of is this 10 blocks per second has been narrowed down as this artificial constraint. And then software was made to operate fast enough. And now actually, especially over the last couple of weeks, there a lot of optimizations come in. The node is becoming like twice faster in different aspects. So already, like the couple of days ago, coder of Stuff, one of our contributors, was saying that his one of his like older computers that was kind of borderline on performance now is able to process the data because of performance optimizations done by all our contributors and people like Maxim. So, however, these performance considerations don't have to apply to L2, especially if you have different L2s. If you can easily have one smart contract platform or two smart contract platforms or contract platforms, and each of them can have their own restrictions and performance considerations. Some might require a lot of memory and operate for specific purpose. Some might require something, other constraints, and some can be actually you can have, let's say, if you hypothetically take something like JD Edwards One World or any kind of SAP system, and you turn it into a smart contract platform state management system, that can be its own L2, just directly operating against Kaspa L1. There's no need, as long as there's a set of predefined primitives in L1 as to how to interface with it. The implementation considerations, the type of L2s that there can exist, we're not limited. And we don't want to be limited by that. We don't want to define any specific criteria because we don't know what the future might bring, what kind of technologies might become available in the coming years. What we do want to do is we want to have the lowest common denominator, the functionality for L1 to function as a ZK verifier, ability to do some data processing. And then also, we do want to venture into building smart contracts and smart contract execution, but this is a whole separate topic there from L1. On L1, we don't want to do that. The technology is really kind of changing, especially in the last couple of years, and especially zero knowledge technology. And I'm going to cover that in a second. So again, since we're talking about Kaspa L1, we're talking about Kaspa SDK. Kaspa SDK is an important component of that. I'm sorry, I went off on tangent again with regards to the overall kind of goals behind L1. But as a part of this effort, the Kaspa SDK is meant to have a number of let's say, additional PC calls and data processing capabilities, such as, for example, right now we can subscribe to different events on the network, such as basically what's known as virtual selected parent change notifications that basically take the early what I showed there, the dark algorithm, and they of the actual raw of the transaction data, and what we might want to do is have a similar interface that would function but be filtered by subnet filter. Um, that depends. It's there's a lot of considerations for that. So one slide I have made in response to some questions I was asked recently. Basically, what is the layering? What is the SDK structure? And in basically in the Kaspa, you have a layer one and Kaspa SDK, and layer one and Kaspa SDK is basically L1, and then you have a data delivery process for L2. That's what Kaspa already can do and does. For example, the KRC, the indexer uses that functionality. Then an application needs to intake this data and process it as a receiver effectively, and maybe organize it somehow. This is already outside of the L1 of responsibility, even though some primitives can be a part of Kaspa SDK's kind of data receiver process. But so I'm not sure. Maybe this will go in between, maybe not. But maybe it will go in L1, or maybe it will be a separate kind of temp. Uh, uh, framework component, set of framework components. And then you have L2 data processing and zero knowledge processing. That's all done on, this is already done on L2. And we have, a while ago, we have, a couple months ago, we have started building and prototyping a layer two project called Sparkle, and this is basically right now an infrastructure shell. While we are working out different elements with regards to L2 actual L1 and L2 specification and architecture of how to implement all of this. And but the goal here is a Sparkle 2 or alternative. This can be anything, anything here. The key takeaway here is that the entire infrastructure is open source stack, and whatever is going to be done on L2 processing components, even if it is outside of the Rusty Kaspa, it will be open source and done utilizing reusable components, so anybody can interface with it. They can either take parts of it, build their own L2, develop smart contract directly on this L2, or basically we want to make it as flexible as possible for anybody to be able to reuse as much as possible for their own implementations. This is one of the kind of ethos behind that is the, if you have a commercial mentality, this is the inverse of the commercial mentality. We want to build and we want to facilitate a framework and infrastructure for users to build L2s. So now we're talking about where's Junior? Is he here now? We are talking about ZK proofs. Bunch of questions with regards to ZK proofs and some people don't really have an understanding of or how this works. And the reality is that this is a very complex topic. It's its own, the domain of science. But what I like to do, but the reality is that at the same time, all of that processing in a kind of gone through in the last couple of years, kind of gone through really transformation, like a lot of technologies like AI and such. And this is something that now becomes much more accessible and easier to use, and developers can utilize that without necessarily understanding all the inner workings. So, what I've got to sharp, if you know what ZK proofs are, and if you're in depth familiar with them, close your ears and close your eyes. Don't look at that. The goal here is to convey the general understanding of how modern ZK proofs can be made to work. We're talking specifically about um, uh, so uh, CK proofs. You create a program equals y, where x is an input and y as an output. You instrument the program obtaining a prover k pk and a verifier k vk. Then with that, you can create a proof pi that fx equals y using the prover key. And then you can verify a proof pi using the basically the input and output arguments x and y, verifier k, and the proof pi itself. So what does that actually mean for a regular developer? Because this might not be as apparent, but effectively f of x, you can look at it as a function, you can look at it as a program. It's any type of code that does any type of processing, and uh, from that you can generate prover and verifier key. You can then, using the prover key, generate the proof, and then using the if you have that proof and you have the verifier key as well as all the arguments, you can then verify that proof, indicating that in fact x and y, given the x and y are specific values, and that the f was a real program, that nothing has changed, nothing has been substituted. So there's this element which is called the ZK circuit. ZK circuit is a specific tool or a technique used to encode computer programs as ZK proofs. It defines the rules and logic that verify a program was run correctly. This can be very intimidating and hard to understand to some people, because you see all of that processing and it's a little hard to do. And this is why I said for people who are familiar with ZK proofs to close their eyes and ears, because I'm gonna really simplify this and explain it in a completely different way, so that basically, if a developer knows how basic programming works, then he should be able to understand, to get an idea about how ZK proofs work. And or at least the instrumentation, well, we'll get to that in a second. So when you create a program, you have a bunch of high-level programming code, let's say C, C++, Rust, or whatever. Ultimately, this program is compiled down to some form of assembly. Assembly is basically a visual, it's kind of the first programming language that was ever there, and it's a visual representation of CPU instructions. So assembly really represents a bunch of bytes that are instructions, byte code that is fed to the CPU. And so here we have assembly, and we feed these bytes to the CPU. CPU does something, and CPU produces us some information on output. A virtual CPU is the same thing as the CPU. It's just emulated in the software. It's a software that takes the same sequence of bytes and behaves like a CPU. It generates the same output. It's a program-made CPU. So, what is instrumentation? The one of the most common, basically, one of the most common types of instrumentation is profiling instrumentation. It's where your code, your functionality is injected with a bunch of other functionality in order to obtain some, let's say, tracking or something like this. So a profiler in instrumentation, basically a simple example of it would be you have my function 1, my function 2, my function 3 that you call in your regular program. But a profiler will instrument that, and what it will do, it will look at every function that you call, and it will start tracking time for this function before, and stop tracking time for this function after. Before, after, before, after. So this is a basic example of like profiling instrumentation. So now we come back to the bytecode instrumentation, but within the context of zero knowledge. And this is like I've made this again specifically for regular people to get an idea. People who know who understand the bytecode but don't know what the ZK proof is, to just get the basic idea about how this works. But effectively, you compile your application and into a CPU instruction into the bytecode. And what a ZK ZK instruction processor, basically a system that is able to create proofs for your programs. What it does is that for every operation that you execute in your program, it inserts a bunch of different mathematical operations. And I'm not going to get into what type of operations that they are. This is all complex. I'll just abstract that as ZK math, effectively. And then you have, once this process is complete, once the setup compilation is complete, you generate the verifier key and the prover key. So then what you can do is, if you have a prover key, you can execute your program, and the program will process all your original instructions, but it will always process what I'm referring to as zero knowledge, basically arithmetic instructions that are instrumented in your code. And when this code has executed, you have a specific value, proof. If you take this value, you mate it with a key, you see whether this proof is verified or it has failed. So the key element here is the instrumentation, because if you the way this ZK mathematics are laid out within the bytecode is, if you change you have your program, but if you change anything within the behavior of your program, if you change your original bytecode, your instrumented bytecode, then the resulting proof is going to vary. It's almost kind of like a hash, but it gets computed as the program executes. And So effectively, this prevents anybody from being able to modify the actual program because the proof will no longer work. So the modern uh, now there are tools available where you can effectively take any program and you can compile it through a ZK proofer, effectively converting any program into an instrumented program, which then can which then can be used to generate proofs. So I hope this brings some light, but effectively. Part of the so there is different something I'm missing here is that there is different target architectures, like there is x86, there is ARM64, which are CPU bytecodes. There is WebAssembly that you can target as well, and there is an architecture called RISC, and there is an architecture called RISC-V. RISC-V is the latest. Basically CPU RISC CPU architecture, which is the key element of it is it's open source, and so it's available to anybody to use however desirable. So a series of tools exist that we'll look at briefly later that allow you to take any existing code, any existing application, and compile to RISC-V architecture. Then this RISC-V architecture gets instrumented by these tools, and then your application becomes provable, which means that you can make a hello world. And when you run, let's say a program that asks the name and outputs the name lowercase or something like this, a simple example. And then when you run this program, you can, given the name that you've given it, given the name that it's outputted, given the actual prover key, you can run it and make sure that the program has not been touched, nobody has tampered with the program. If you change basically anything in this program, the proof will no longer work. The key element I'm trying to get to here is that any existing application can be any existing application that does not do external interactions like file I/O or networking interaction and such can be compiled into a provable application and to generate the proof. One of the examples I gave today, for example, is if you take something like Quicken, again, abstract and simple example, but if you take something like Quicken, an accounting software, and the company builds makes a provable accounting software, it kind of passes that through this process, and then it sells it to all the customers, and each customer who files their taxes then takes their taxes and sends the government the data from their taxes as well as the proof value, and the government verifies that. What that means for the government is that nobody has tampered with the logic of the Quicken software, that the software itself runs as it was created. Nothing has changed in it. So it's the software is authentic. And this projects into basically into smart contracts, that now you can have different application code where smart contracts can be provable. That means that if you have a smart contract, you at the time of its let's say creation, you publish that this is the smart contract, and you generate all these different elements such as prover key, verifier key. This smart contract cannot be tampered with. Anybody can have it as long as anybody runs the proof and it results in the same data that you can verify. That means you have not tampered with the program logic. It's authentic. So now it's getting very late. I'm pretty tired. I'm doing my best with the band and such, but I'd like to cover a bunch of research that is happening in the area of layer one and kind of layer two. The research in L1 and ZK proofs and related elements is led by Jonathan Sampolinsky. But there's different layers to that, and uh, uh, I am I'm trying to sort of in the process of trying to understand different constraints and requirements and work upwards toward the kind of original design and the requirements. And I'm trying to bring the design and requirements together in an effort to work out all the kind of basically identifying the potential vulnerabilities, all the performance, but the potential performance bottlenecks, all these different elements in order to ultimately create a spec which we can follow on L1 to create a this kind of what I described as a L2 agnostic system that will work against any type of L2. So everything following this slide is subject to change. This is just exploration of different concepts and designs. I'd like to also thank Maxim a lot for helping me in working on that. Uh, First of all, there's notion of reorgs in the Kaspa, and effectively, if you have a the ghost DAG is a deterministic ordering algorithm that processes the blocks, but ultimately results in a merge set. The reality is that you can receive a bunch of blocks, but then some blocks can arrive just a little bit later. When they arrive a little bit later, for example, then the ghost DAG output might change slightly, and that can result in a reorg. Effectively, the selected parent chain might change as I'm illustrating here in the example between first and second, and then you also that can there's a new block arriving, and that in turn can affect the merge set. So one of the problems is one of the problems with proofs is that you can post proofs on the network, but then you can have a reorg and what which changes the transactions before the proof has been posted. So which you will then have a valid proof, but then you will have maybe some sort of an invalid state. So one of the solutions for that is that, or one of the approaches for that is that the blocks on the selected parent chain currently they have Merkle root of its own transactions and the Merkle root of uh, the merge set that this block represents. One of the things that can be added to that is a merge set of a rolling hash. Is a hash of a rolling hash of merge set combined with the previous rolling hash of a merge set on a selected parent chain. Effectively, that you have this block includes all its merge set hash of its merge set transactions, including the hash, including this merge set hash from the previous block. Next block also includes all of its merge set transactions and the hash of a previous block. And we kind of use selected parent chain to kind of create a stacking of that, and this way, if a reorg changes and anything related to merge set gets invalidated, the system will rearrange itself according to consensus. But one of the things you will have here is you will have a cascading hash invalidation where this hash will propagate forward. And if this, so the idea basically is that if you have if you're generating ZK proof, one of the inputs to the proof can be that merge set hash. This way, for example, when you post a proof, you take the latest known block and you take latest known selected parent chain block. You take its merge set hash and you add it to the proof. This way, if a reorg occurs somewhere before that, basically it invalidates the proof, making the transaction itself invalid. And obviously monitoring would need to occur to handle that. So now I'd like to slide basically quickly cover, there's two models that are possible within ZK proof, basically layer 2 and subsequently layer 1 that needs to recognize that. A single state model and a multi-state model. So as I mentioned before, UTXOs can carry states, a hash representation of accounts. So basically, do you have one all-encompassing state and account and everything in it, or you have multiple states and everything, and completely segregated for different purposes, let's say. The let's say so far, like Ethereum rollups and layer 2s on Ethereum, what they do is they generate one state. They load all the information within one program. That program is a provable program. They do roll-up processing, and that's that. It's all one thing. However, you can also have multiple states, effectively multiple accounts on L2, where each account represented by a specific state. So to efficiently handle states, it's beneficial for L1 to support multi-state model, where a single L2 can on demand create multiple states, effectively substates. They don't have to be states; they're actually completely parallel to each other. Each state, if desirable, can have its own Kaspa balance, because we one of the requirements sort of for rollups is that we want to be able to associate balance with a specific state. We want to be able to send balance on L2, and then this balance can be used by can be transferred all in one using L2. So such model allows for parallelism on L2, because you can have states that are completely independent can operate completely in parallel to each other. There doesn't need to be a hierarchical relationship. There can be, but doesn't have to be, because if you look at it, if you have an L2, L2 can be represented as as a single, let's say, as a state or a set of state. Then another L2 can be represented by a state or another or a set of states. But you can also have a single L2 that just has a bunch of states published on L1. It should be it should be the prerogative of L2 to determine what states it wants and how many states it wants and for what purpose. That's one of my key assertions, is that L1 Kaspa should not be, even if L2 uses a single state, L1 should not be limiting state processing to be somehow as already that's a part of the design, because you can have multiple L2s, but we'll get into that a bit more in depth now, because the reality is that you can also prove multiple states simultaneously. What are the benefits of multi-state model? Which is that there's you can let's say you have different program calls and you can generate proofs for all of them continuously, or you can break proofs down into shorter executions, or you can do proofs down on separate sets of states. So more states provide effectively ability to have more granular exchange with L1, which means more frequent transfer of funds on L1, more frequent communication between L2s, because you can post, let's say, as in a classic ZK rollup, you can post, here's the information, here's the balance, give out the money to these accounts, because I've provably concluded that, or here's some data, interpret data how you want, and this data between L2s, if there is any proposals, let's say, for standardization, then this data can be used as, let's say, bridges between different L2s, basically direct data exchange, DDE. Another thing that multiple states, and when I'm talking right now, I mean multiple states and short-term proofing also. Allow is potentially, again, this is all research, and some of these elements, like some of these elements we were just discussing and kind of originating in the last couple of days with me and Maxim, as we're trying to address different elements of this and understand potential shortcomings somewhere. So we can have a proof of work like proofer ecosystem. We'll get to that in a second. And the drawbacks of more frequent proofs are the associated costs. The problem is that whenever you want to prove something, you post a transaction. Whenever you post a transaction, you are paying fees for the transaction. So if you start, the goal has to be some type of a balance between the intake. Basically, whenever you call a smart contract, you might want to collect some fees for that L2 operation. When you collect these fees, then you might want to post proving transactions, and there can be rules associated with that. But if you start posting proving transactions all the time, L2 will eventually run out of funds. So the just let me kind of skip onto this slide, which is the multiple reward-based provers. The one of the key elements or challenges in that type of L2 design, proving design, is who does the proving. The proving requires a lot of computational power. It's slow, and why would anybody do that? There is an argument that whoever makes L2 would want to support the L2 with proofs. That's straight out centralization. That means that the second the car hits that somebody, L2 will cease to function. The goal is to have some form of decentralization, and this is why I'm trying to kind of bias that in this direction, trying to find a variety of solutions on how to do that. So there can be there's basically hold on a second. Can I describe this? All right. So one of the things that I sort of skipped here with regards to proofs is the idea where basically similarly to mempool selection on similarly to entropy-based mempool selection on the in GOES-DAG in the proof of work processing. What we can have is, let's say, some way where L2 basically says, here I have 10 different proofs that I need to be proven. Let's say some by some mechanism. We have a bunch of proofs that needs to be proven. What can be done then is that the smart contract can have different arguments, different inputs and outputs. One of the things a proof miner basically, let's assume that there is somebody who's interested in generating proofs. What he can do is he can take the proof, so he can take his address, his basically reward address, and he can add that to the proof, and then start generating this proof. He can add that as one of the smart contract inputs and start generating the proof for that smart contract execution, or a sequence of, or whatever this proof represents, maybe multiple executions, some basically sequence of operations. And if we have, let's say, 10 proofs that need to be generated, the proof miner can come and say, I want to, give me the next proof, and the proof that is selected for him can be random. So basically, all the proof participants can have random selection of which proof to generate. They then, slightly similar to PO proof of work mining, inject the address in there, generate the proof, and then basically first come, first serve. Whoever manages to generate the proof fastest, he will produce the proof that is valid, that also includes his payout address. There's probably some vulnerabilities in there, but and obviously the most powerful miner will dominate this ecosystem. But this is currently on that side, the vector that I'm trying to research, to understand if that kind of schema is possible. There can be different processing. So if there is let's say, there can be short-term periodic proofs. There can be multiplexed proofs. Effectively, each smart contract call initiates a proof generation for n's previous smart contract execution. So you have a kind of rolling parallel proofing, but then the transactional cost becomes too high. Another approach to handle this is basically a proof of stake selection, where you can have a proofing miner selected using some form of proof of stake algorithm, or let's say can also be deterministically from the DAG potentially. Just let's say there is a registration that DAG acts as a deterministic random number generator, sort of. So when I mentioned that there's multiple states, and that means that multiple UTXOs that can carry multiple states. The problem with that is that, well, not the problem, but the issue with that is that you can have one proof. Let's say you have a simple transfer between two accounts, and accounts are two different files, and there's a program. So you have a program, you have account A and account B, and you can view account A as a file and account B as a file. So what you need to do, you need to move from account A. You need to actually take the funds from account A, you need to subtract the value there, and you need to add the value to the account B, controlled by that one program. You don't need to construct, this can be done atomically, and this can affect only, let's say, this account. So you have three participants, and the common denominator is the program. This program, let's say, controls these two accounts. So any exchange between these types of accounts, let's say, is done by this program. But regardless of the pattern of use, the issue that arises is that you can have basically multiple UTXOs that represent states, but these states are but you have one, but you can have one proof that takes multiple states. So how, if you have multiple UTXOs, kind of traditional views on ZK verification is that the UTXO, you can have an opcode to process the UTXO state, but what if you have multiple states? So one of the approaches for that is to have a specific, basically a payload-based VM, a specific set of opcodes in the that live not in UTXO script but live in the actual payload. And when there is a ZK proof transaction, then the setup for the proof, basically the payload script can be engineered in such a way that he constructs all the data for the proof verification. For example, if you imagine this transaction with the payload, now the payload has a script, and the payload goes, okay, reference me first input, reference me the second input, reference me the output of the transaction. Now we're gonna utilize a specific type of proof, because there's different types of proofs in zero knowledge. Basically, select the proof type. Let's say load the verifier key from that UTXO. And there's a couple of issues with that. And then load the proof itself, which is in the payload, and now verify the integrity of this entire transaction that was created by this smart contract. Basically, all the inputs and outputs of the transaction, all the data in it is aggregated into this almost like a cold data structure, which is then verified by the proof. So this is the concept behind the payload-based proofing scripts. The key point here is that it's not the standard UTXO script VM that does this validation. It's a different type of VM with its own set of processing that does that. So then there is a bunch of other potential opcodes, such as basically ability to create state, ability to effectively. It's unclear right now how all of this will integrate, and how these concepts will, whether they will take hold or be adopted. But the general idea is, if you create a state, you are creating effectively a subnet. You are creating a new L1. Any state that you would then create needs to be provable. Effectively, every interaction that related to states needs to be ZK provable. That L1 basically dictates that, hey, I have created a new state. I have made a new account. Here is something new happening, or I have deleted that account. So the basically opcodes for state management would then can be available inside of uh, standard transaction VM script, but they really would be more of a verification nature, because the proof would be generated by the payload. So these opcodes would more act as a sanity check. Another so now because what we're trying to effectively do now is we're trying to create create schema with opcodes and proof generation, which using existing infrastructure as well as new infrastructure allows to simulate, and given the concepts of UTXO state, allows to simulate basically smart contract, the bare minimum needed to simulate a smart contract execution needed for the roll up within the context of UTXO driven DAG-like network. So there is state balances, which is the methodology by which you would basically delegate Kaspa to layer 2 contracts, and then be able to for when the layer 2 tells layer 1 to disperse the funds, layer 2 would actually create the actual transaction to disperse the funds, but that transaction would have this pay from state opcode that would allow a balance on the UTXO carrying state to be spent. And this type of opcode would be usable only in a provable transaction, for example. So this is a mechanism where you call contract, you delegated some Kaspa. When the contract is being proven, or where the contract wants to do a payout, then the uh, these opcodes can be used to facilitate the payout from the balances kept by UTXO. When we account, basically, if we look at an account-based L2 system, you can have an account can represent data, but an account can also represent program. It can represent some code, and this code is the actual smart contract. It's a program that you upload into L2, and then you interact with it. Are we dying? So one of the basically key observations here is that if you have a data account, a state account that contains data, uh, its state representation can be any value such as a hash or a Merkle root of its data, whatever you want it to be. However, for the program, this state can be a combination, first of all, a program hash. I'm not sure if that's needed, but most importantly, it can have a verifier key. And because to verify the program execution, to verify the proof on L1, the associated basically account containing the program needs to retain the verifier key. So effectively, you publish smart contract, the L2 processes it, and when L2 processes it, it creates a state, creates a new account, but it creates a state within L1 that contains the verifier key of the actual smart contract. Whereas if L2 creates a data account, it creates a state with data. So how subnets can be handled within the context of L1 is unclear, but I think this is relatively simple because this can be done. This can piggyback on the existing UTXO index. Some questions still to be answered there. There might be some missing data linkage. Another sort of question in this domain is if you one of the problems that currently exist, let's say, uh, with Kaspa-WASM KRC20, if you need to do some minting operations, some of the transactions have minimum fee requirements. If you send a transaction that does not meet this minimum fee requirements, this transaction will be just basically ignored. In a process, you will lose all the Kaspa that you have sent as a part of this transaction. This is problematic. What you want L2 is to be able to define that, hey, if you're calling me, let's say I might want to collect some fees from L1 for me to maintain the proofs. Like this ties into the incremental decentralized proof generation model. So one of the things that we currently don't have in the design that would make sense to address is that if there is a subnet index and a subnet represents L2, then for example, the subnet can have a minimal fee rate associated with it, where if transaction does not a fee rate, but a minimum fee, and the transaction has to delegate that fee to the state that it's executing. And unless it does that, the transaction would be then rejected at the node level. So if you make an RPC call to the node, you cannot pass through. The transaction won't get accepted because it doesn't meet the some of the layer 2 constraints. So this is some jumped here, but it's renamed. The general idea, basically, there are two types of models in smart contracts. There's gas-based, gas fee-based models, and there are upload limit based models. For example, Ethereum operates on gas based model, whereas Solana operates on upload restriction. Uh, based model. What that means is that since every contract is bytecode, for every instruction that you execute in Ethereum, you pay gas. However, on a Solana, you have 200,000 opcodes, and if you pay this 200,000 opcodes, that's great. If you under this 200,000 opcodes, that's great. If you surpass that, you need to execute the second transaction. If smart contract logic becomes really complicated, it's really has a lot of different conditions. It becomes very difficult to utilize the gas fee based model because you never know how much gas it will take. Like like imagine it's like basically if you have it's kind of like, I don't know, a gas car versus an electric Tesla car. Like if you don't know where you're gonna go, and you fill up you never know how much gas you need. You can kind of have a range, but whereas with the electric car, you know that maximum you can go is that far, so you can reach these specific distances. I don't know if it's a good analogy, but effectively, it's much when it comes to a really complex logic, it becomes much inside a smart contract. It becomes much easier to model logic based on transaction separation versus to model total gas consumption. And yes, your gas, that unspent gas is returned, but you just don't know how much a user will be paying. For one thing, he might be paying something. For another thing, he might be paying something else. Whereas if you have um, fixed costs, it's easier for the developers because you know that you could do that much things, and it will cost you fixed amount. So it's much easier to deal with. So, running way out of time, I'm quickly going to cover research and prototyping that we are working on. So the goal behind this project is this is now basically a group of ad hoc developers that formed around this. This is not this project is not core responsibility. Core is a specific group of developers, and um, the main goal of core is L1. So we want to keep it this way. We don't want to focus on L2s. There's plenty of teams and people who will take technology, and we will help them build some of this technology to build different L2s. Like I said, everybody is welcome, but we don't want to burden the core themselves, because the core of responsibility is continued performance engineering of L1, as well as other L1 specific elements. Uh, but obviously, right now we're in a bridge. We're kind of at the bridge where we need to identify all the patterns, use cases for L2s, and create specification for L1 for core to implement that interface for L2s and make this interface as versatile as possible. Although, like I said, the key element here is versatility, because we're not looking. Nobody wants to make an L2 a smart contract system. That's not what we're looking to do. So at the same time, we have to do it because sort of how do you how do you make a car without the engine, or an engine without the car? There's a two. We need to build a prototype effectively to make sure everything is working. And that I'm saying from the standpoint of a practitioner, as a developer. Like it's very hard to make something. It's very hard to. You can make a server kind of without a client, but making client without a server, that's difficult. So it's kind of midway solution. So anyway, coming back to L2, the goals behind that Sparkle project is to develop a bleeding edge RISC-V and Cairo smart contract platform, as well as supporting other implementations. Deploy ZK EVM capable of supporting existing EVM projects. This is a lower priority because that requires other elements, and EVM itself is not as potent of a system. The reason we would want to adopt EVM, ZK EVM, or maybe somebody else in the community would want to work on bridging that once ZK proofs are properly done, is for adoption of, is to open doors for existing EVM-based projects to join Kaspa network, and provide an integration layer for different types of zero knowledge stacks. So while L1 has neutrality to L2s, anybody can build L2s with their ZK stacks. In the case of the Sparkle project, the goal is to have neutrality toward ZK stacks themselves. So anybody can basically come in and do an implementation. So one of the sort of structure of the kind of ecosystem that I have put together, where the Kaspa kind of stack is represented in terminology of network stack, where you kind of have Kaspa-L1 with raw payloads as just a sequencer and a data carrier, which already is sort of being used. This is UDP. This is analogous to UDP. So effectively, the KRC-20 are trying to use UDP kind of functionality, but there's still things missing there, because that's why it ended up being inscriptions. Then Kaspa-L1 with payloads and ZK verification, maybe some call data SPI, structured data elements. Now we're already talking about TCP, more mature structured data exchange, and then come different layer two. So Sparkle is just one of the layer tools, which is equivalent to BSD sockets. You can have Windows sockets, you can have any type of socket libraries, and then ZK stacks underneath are kind of like different protocols for proof verification. I don't know if it's a good analogy, but at least that's my attempt at it, to kind of signify maturity, even though thematically it's not quite that. So the another element about so L2 is the fact that it's meant to be a dual node architecture. A dual node architecture is effectively if smart contracts are built into basically the okay, did we no. So where was I? Second, is it working? So if you take a smart contract as a small program and you compile it to RISC-V, it becomes a binary that is just a program that can run on RISC-V processor, or it can run on any processor in a virtual machine. And a virtual machine, it can be that RISC-V VM. We already have. We have been experimenting with a operating fully featured RISC-V VM on its own that is very high performance outside of ZK ecosystem. And the general idea is that you only need proofing to settle on L1 or to do data exchange on L1. But if all your data, if you are listening to L1, uh, all the data that you're collecting as a sequencer, all the data that you're collecting from it is authentic. It's what is meant to be for L2. So if you simply power up L2 node, kind of listen to L1, aggregate information from other peers on L2, and possibly utilize proofs somewhere, you have a very high performance L2 node that you can power up locally, and you can power it up locally and interface with it. So you can have your own local node for the purpose of communication with to getting the data, aggregating the state accounts, interfacing with the actual node, effectively creating the local pipeline for your applications, or you can also basically request that uh, the there's a number of scenarios here. You can ask the same node to generate proofs, or you can have a dedicated proof generator node that just focuses on that. But the idea here is that if you're only interested in data replication, data access, you can just rely on all the data. Uh, so the Sparkle multi-account system would be the current goal is to have a PKI system. Effectively, every account has public-private cryptography, and and then there's a variety of there's a variety of research happening right now in regards to, or we're trying to analyze different patterns of execution with regards to using different accounts and whether there would be a basically a central Merkle root of all account data, whether this is needed, how the data can be parallelized, uh, whether there is a way, basically, maybe a more appropriate methodology would be to have different multiple roots, and then to have ability to have multiple roots, account sets. Basically, this is currently under ongoing research. The accounts in Sparkle can be two types. They can be code representing a binary image of the smart contract, or they can be data up to m megabyte in size. Data is just raw data buffer. This is the lowest level common denominator that allows code to access this data and manipulate it however it wants. There is another type of account that we're looking at is potentially indexed, which can have tracking and processing reduction for multiple account sets. One of the things that Sparkle needs within this whole context is an API, and it needs this API within each zkVM platform. Effectively, API denotes, let's say, random number generator, access to the current time, however it is represented, whether it's the score, debugging log infrastructure, and cross-contract invocation. I'm going to get to that in a second. API also includes the execution itself, deserialization of the call data, payload intake, as well as ability to create transactions that are going out on L1 proof transactions. Everything is meant to be atomic. Basically, when a single transaction executed on L1 is meant to invoke a single transaction, a single smart contract execution on L2. However, cross-contract invocation is problematic within the domain of ZK right now, because you have one program, and as long as this program runs, you have a continuous proof effectively. If you exit this program to run another program, then you're exiting this kind of space where you are proving, and now you're somewhere in the unknown. This information might be not provable. If you run this other smart contract, technically you could have that generate a proof, and you could integrate all that, but generating the proof on a basically cross-contract invocation can be very expensive, depending on the pattern of use and what's involved. So maybe ZK recursion can be used here. I don't know. This is one of the currently one of the hot topics in the whole basically ZK ecosystem, and it is also possible to use some type of a protocol on L1, similarly to a custom data-driven bridge, where you would, let's say, if you want to have a bridge between two different L2s using ZK proofs, you could, in a similar way, facilitate cross-contract invocation within the same L1, but it's unclear. So this is still, again, areas of the research. So I mentioned before opcode limited execution. Contract data, account data requires storage. Storage means bytes cost. There is a variety of platforms. This is a common problem in cryptocurrency. Variety of problems of platforms use different methodology. We haven't zeroed in on what approach to take here. Very possible temporary rental, as well as very possible permanent rental of the account data that grows the disk space. So this is more about, this is not as much about research as much about decisions. One thing we have not really looked at is there's a variety of platforms, like for example Saya, who have who generate proof of ownership of storage, and using this proof for ownership as a payout mechanism for proofing. Maybe ZK can be applied in this domain if it can. That would be very interesting, because if you have, let's say, time-sensitive challenges or some kind of POS mechanic, which allows L2 to prove to the network that somebody owns, that somebody owns the data set, the state of the entire L2, and it is provable at that time that he owns it. Basically, participants can be rewarded for maintaining the nodes, maintaining the nodes with storage. But this is unclear, and this is really outside of the right now current focus. So when we come to ZK stacks, currently we are exploring basically SP1, Risk Zero, and Cairo. Risk Zero and are the two primary areas of focus. Risk Zero is the basically originally risk, basically what I have been describing before in a simplified manner about the RISC-V instrumentation. The Risk Zero, they provide that. SP1 also does that, but and both SP1 and Risk Zero, they process RISC-V bytecode. They operate on top of RISC-V bytecode. Cairo, however, is have proprietary technology. It is very similar to basically Cairo programming language has its roots in Rust. It's very similar to Rust, if not almost identical, with certain additional elements. And the interesting thing about Cairo is that unlike RISC-V, they generate their own assembly instruction set. They have their own basically bytecode for the CPU, for the virtual CPU, and some of the problems revolve around some of the challenges that ZK ecosystem currently experiencing is different challenges of instrumentation of the bytecode, which makes proofs which do not allow efficient proof acceleration, and like SP1, one of the solutions to the, let's say, performance issues on RISC-V processing is modifying the actual RISC-V bytecode to introduce ZK specific instructions in there. On Cairo, however, it's a proprietary instruction set. And because it's a proprietary instruction set, it allows much faster implementation. So there is the reason we want to be agnostic to the actual ZK stacks is because we don't know what to expect in the coming years. There can be different technologies evolving. Risk Zero has an open source GPU stack, which allows GPU-based prover generation much faster than CPU. SP1 have a closed source GPU stack, whereas Cairo has, for example, they're in the process of building and releasing a new prover, which is going to be 3 times faster on the CPU, and then they will also have a GPU based proof generator. The sorry, I'm almost done. I think this was Right. So the other there's a variety of stacks, and so this is why we want to kind of be stack agnostic and work with everybody. And Delphinus is another alternative, but they do risk 5 for Seattle Cairo assembly. They do web assembly. So basically, there's different bytecode interpreters. There's different solutions to all of this, and different performance for provers as well. The reality is that the goal for the uh, code segment is not to define is to define what type of prover should be used, what type of bytecode it is, but not rely on but be agnostic. So effectively, you should be able to, if you have a ZK system, you should be able to use the ZK system and build an application, build a binary, build a smart contract on it, upload it to L2, and L2 would use the appropriate proofer, etc. But obviously, as I have mentioned, types of proofs. L1 needs to be aware of the types of proofs, which all of which can be gradually introduced with through the basically hard fork management. So I mentioned earlier we also intend to power up ZK EVM. There is a ZK REST Ethereum client, RETH, which can be built with a as a ZK system, and the question is mating it with basically Kaspa block diag processing. Um, uh, which is we would need to have a custom tool chain for Rust to handle smart contract deployment management, as well as basic standards for standard fungible and non-fungible tokens. Uh, Sparkle SDK uh, would also provide for let's say fungible, non-fungible token standards. There would be a variety of integrated serialization, deserialization data to provide access to. So, well, we can. Well, there's one slide sort of left, but otherwise we can call today. So, so to sort of to do presentation. You guys, I hope this was interesting. I can see to some it was. The we went over to first. I think any business manager should focus on adoption of Rust. It's really great for interoperability and the efficiency of development teams. We kind of briefly went over various aspects. Yeah, that's fine. Yeah, just that's the last slide anyway, so leave it there. The requirements of L1. Basically, we're looking at various variations and models for L2 design, and what I have presented right now on the L1 architecture is highly driven uh, by this set of requirements that we see on L2s. I hope Jonathan won't cut my head off. That I have not, deviated way too much. This is, in part, this is an open forum and brainstorming session. I'm also using that to sort of kind of address some of our developers on Discord to sort of present the information. I hope this has been useful to them, whether it's on Rust or on the whole smart contract ecosystem. And here's basically this is the last slide of the previous presentation on the Sparkle, where you effectively what you have is a peer-to-peer network. Each node. So the important thing here, while each node is represented as if it's talking to L1, the important thing is that basically L2, at least Sparkle, will have a Kaspa baked inside of its application. Same way as Kaspa-NG does. Kaspa-NG powers up, it can power up Rusty Kaspa as a child process daemon, or it can just start it within it can start it as a thread. So the same thing will be here. It will start as a thread, connect to Kaspa, and you will have a single application that will run, that will interoperate, that will do peer-to-peer communication and consensus processing. That will be Kaspa, and tightly against it, there will be Sparkle interfacing with that. Once again, I want to stress very much that this is not a uh, this is the goal behind this project, and I'm sure the Discord and our developer community will back me and can relate, because what we have done in the wallet ecosystem, we have developed the wallets and then made everything as accessible as possible to the wallet developers. The same ethos is meant to be applied here. We want everything to be, first of all, to follow both on L1, whatever work is done on L2. We want to follow the Rust standards established by core, same mentality. At the same time, make everything as modular and as adaptable, so that any parts can be reused. And I will, however, again reiterate that attitude stance is very beneficial. It is very beneficial for Kaspa, but what this can result in is a fragmentation of ecosystems. This is why I'm so much stressing the whole aspect of data across L2 data exchange and potential development of protocols and things that we can think about to address that. Because if you have many solutions, they need to talk together. Otherwise, you'll end up with Babel as the ecosystem. So on that, conclude my presentation. That's it for tonight.